Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to quantum computing. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific networks built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
We are all looking for something. Some of us search for treasure, some for inspiration, and some are looking for that which can be found in our. Welcome to the Multimedia University of Kenya ICT Museum, the only one of its kind globally. Visit the main campus and be taken through the telecommunication evolution. For more information, visit our website at museum.mmu.ac.ke. MMU Museum, where the past meets the future.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics, and the nurturing of sustainable science for all. ICTP's founder, The Nobel laureate Abdus Salam believed that science is the common heritage of all humanity.
Yes. Sí, sí.
From climate change to quantum computing,
Blah blah blah. Yes, yes.
Hi, David.
Hello?
Now we are getting you.
Okay.
Okay, good morning, everyone. Welcome to the International Day of Life. Today is the day of International Day of Life, and we can start now with our first speaker. It's Dr. David Wazwa. He is a lecturer and researcher in optical communication, and he used to work at University of Eldoret in Kenya, and is now a senior researcher and acting director of the Center for Broadband Communication in Nelson Mandela University, South Africa. Today, he will tell us something about optical fiber communication technology. David, you have 2 hours, but maybe we can split in 2 halves. After the first 50 minutes, maybe we stop for questions. What do you think? Is that okay, David? David, maybe can you try to... Again? David, you try to speak. Can you hear us?
I'm getting you.
Okay, good.
You can give your.
Dr. David,
Yes.
you have been requested to continue. You can proceed.
Okay.
Yes.
Okay. Sorry for that. I didn't hear. Good morning, everybody. Yeah, I'm very grateful for this opportunity I've given unto me to make a presentation. Yeah. Introduced. I'm Dr. David. Yes, I'm the acting director at the Center for Broadband Communication. But I'm actually a Eldoret. I want optical fiber communication technology. This morning, I have divided into two. I'm going to look at the first part of it is about the basics of optical communication. And then the applications, I will touch part of it a little. And then bring in Dr. James, who will be sensing. I might take 1 hour or less, depending on how fast I move, but I had the introducers able to stop. I don't know what time, but you can be able to inform me when you want to stop, so they can be able to stop. So my table of content is as given: an introduction, the basic of optical fibers, optical transmitters, optical receivers, and then applications. First slide is showing us on how the optical network is snaking through Africa. We have mile a greater terms of networks, and whatsoever you see in yellow, in orange, it is the active fiber that is already being used. The concentration is so much in the southern part, and then partly in the eastern part, and partly in the western part of Africa, the orange part of it. The red part of it is where the construction is still undergoing. Quite an amount has to be done for us to cover the remaining part of Africa. That means there is a potential still for us to do some work in this particular area for a longer time. When you look at the internet penetration, you will realize according to compared to the world connection, only 6% of Africa has been covered by 5G connection. So that means we have a lot of to cover of connection and the latest technology. But nonetheless, we are at least somewhere compared to the time that we started initiating this process of optical communication around 2010, 2011 in East Africa. I still remember the slides that I used to make for communication in the early 2000. You could be able to see actually the dark part of Africa, but now it's becoming much at this particular moment. So the history, the light kiting was done by Tyndall in late 1800s, and it was the first one that was being done at that particular moment as a communication, just to guide distance. And then we had followed with the dielectric waveguide analysis in 1910. And then early experiments started flowing in 1930 with silica fibers, when they discovered that actually silica fibers are good as a waveguide to guide the lights. But still the attenuation was very, the absorption with silica fiber by then was very high. The image transformation by fiber bundles was done in 1950. We have covered much of a mile until in 1970 that we had the first fiber with less than 20 decibel per kilometer loss by coning in 1970. Imagine 20 dB per kilometer loss. If you have a lesser source with a 3 dB and you are losing 20 dB, that means your receiver sensitivity must be very good for you to carry the signal through. Otherwise, you might end up transmitting next to 10 meters or so at the end of it. But the record low was set in 1979 to 0.2 dB per kilometer, and that formed the standard optical fiber at the beginning, which has remained the standard optical fiber. That still remains at 0.2 at this particular moment. When you look at the legacy fibers we have that we laid earlier on, it has a 0.2 dB per kilometer. The breakthrough for longer distance came when they discovered the amplification at a specific wavelength. They discovered that APM doped can be able to amplify the signal within the window of 1550 nanometer. That is the time they translated from 1310 1550 or 1310. So that one gave a breakthrough, and the reach was extended and the speed increased. That is how the technology started accelerating from there. That's around 1987. The Holy fibers were first proposed in 1991. That the Holy fibers were first proposed in 1991, and it has been accelerating ever to higher heights. The photonic crystal fibers, which are becoming key at this particular moment when you look at in terms of them are using photonic crystal fibers because of the main core that they can be able to transmit. In that case, the power is high enough. The band in fiber 7, and most of the last mile at this particular moment, the fiber to the home, fiber to the hub, is using the band intensity fibers of the small radius band that can allow so that in that small radius band has actually accelerated the access network technology at this particular moment. The next one, I look at the basic of optical fiber, that is what type of fibers do we have on the market? There are various types of fiber we have. We have single mode and multi-mode. And the single mode depends on the structure. Even multi-mode, it depends on the structure. And in that case, the function is different for different fibers. One we see is the single mode step index fiber. We can be able to couple the fiber to the core and transmit most of the power into the waveguide without much loss. Though we still have losses, yes, but the losses reduce because of the stepped indexed, the way it has been done. On the fiber, we have the core, which is the center that light that passes through, and then around it we have the cladding that within the cladding, between the cladding and the core, it determines the light to be moved within the wave in such a manner that it has to be able to achieve the condition of total internal reflection. And as for total internal reflection, the refractive index of the core should be slightly refractive index of the cladding. I think as physicists, we understand how that one comes about. I don't want to labor to do that. We have to cover the fiber for protection at the end of it. So we have the single mode fiber that we are nearly transmit a single spectral line through, though in reality it's quite hard to have that single spectral line, but we are moving to that. The other one is the multi-step index fiber, and the multi-step index fiber, we still have the cladding and the core, but the diameter is much larger in the way you can couple in many spectral lines. And in that case, so the transference must the one for single mode fiber. The other one, index fiber, which has a sort of a spherical core. You can be able to have a beam radius much bigger than the one for stepped index. Is we get that the angle of coupling is much bigger, and we can be able to have in, though with many spectral lines. We come and look at the numerical aperture, the most important factor that can be able to use to manage the light into the fiber. When we look at this diagram, it explains the physics that is applied for the light to go through. We have the red line that to the core. But the blue line, at one particular moment, some of that light can be able to penetrate and into the cladding. So the numerical aperture is an important factor in launching the light into the fiber. And in this case, is determined by looking at the difference between the refractive index of and synoptical fiber is determined by what we call the V number, and the V number is a function of the numerical aperture. So in that case, the number of modes depends on the wavelength, and it also depends on the difference in refractive index. Now remember, if we look at created the is quite big. Is quite big because the cladding mostly is very thin, and it looks like we can be able to have a very large numerical aperture. So for single mode, we endeavor to ensure that the V number is less than 2.4 for us to have only a fundamental mode being transmitted. A fundamental mode being transmitted. The other modes cannot, we can be able to ship it to be of in refractive index. But for us to be able to have a multi-mode, and then our V number should be greater than 2.405. In fiber, we have various distortions that can be able to affect our signal as it goes through the waveguide. Majorly, we have the dispersion and we have the attenuation. The dispersion is divided also into two. We have the polarization dependent dispersion, and we have the chromatic dispersion, chromaticity of the light that courses through. In telecommunication, we always say it is good to minimize the dispersion and that for us to have a longer reach and to increase the speed the speed of data transmission in that case. So here I show on the screen where we have our signal is supposed to go through the waveguide, and this signal, if not managed well because of dispersion, it will reach the end that the signal has been prudent. And once the signal is prudent, and then in that case, you realize that there's fast-moving spectral lines and slow-moving spectral lines, which can easily confuse that detector. At the end of it, the data is not readable. So it might be able to need some correction of it. So the chromatic dispersion is divided into what we call material dispersion due to the making of the material, and the waveguide dispersion due to the structure of the waveguide. And this one is easy to compensate because if you look at the spectral lines, the best thing is to generate a system that can be able to spectral lines and to fast track the slow moving spectral lines so that we can be able to have the spectral, the pulse be able to come back to normal from the product position. The other one is polarization mode dispersion that has been a problem for long, but it has been managed as time goes by. I remember this was the first investigation we were doing in mid 2000. We are dealing with polarization mode dispersion in fibers in legacy fiber country, and in the mode dispersion, look at the light that goes through the fiber. Our assumption core is circular, but sometimes you realize that the manufacturing process has been laid or is elliptical, and it's elliptical, and then we realize that it has the first axis, the major axis. So when you couple the light through, light aligns to the first axis and light aligns to the slow axis. And light sees different refractive indices in the two axes. So as it moves through, because of the different refractive indices in the two axes, you realize that the speed is different, and light reaches at the end, it has different polarization, majorly resolved to two. In that case, you'll see the fast moving and the slow moving due to polarization change. And we measure difference between the two. If you want to know how much dispersion due to polarization has been done, measure what we call differential group delay. The time delay between the coupled light that was split into the first axis and the slow axis, or the major and the minor axis, ellipticity. How do we be able to manage this? There are several ways to be able to manage the polarization, because it is true that always is aligned to a particular polarization. And when data reaches at the end of the mile, you realize that the polarization has changed, and then the data likely has been distorted. So the fiber design improvements, there are several ways has been done. Through the manufacturing process, they have tried to lower the intrinsic the stress, so that the fiber that is coming out, it can be able to absorb much stress without bending or without deforming it, which has really helped so much. The other one is to look from the component point of view and look at what do we do to control the polarization. And then there are devices which are called polarization controllers that we use to align the polarization. We can be able to couple as much power in a particular axis as much as possible. At the beginning of the and at the end of the fiber, we try to align the polarization so that even if it is distorted, it can be able to come out most of the power coupled in the polarization according to the alignment of the axis. They have to look at, they have to improve the distortion by using polarization diversity receivers, which are quite an improvement, and has really hugely been able to improve the speed of transmission of the data. to a large extent by using polarization diversity receivers, whereby you can be able to have the polarization the data on a x-axis polarization or x-axis polarization, and then at the end of it, you also align the axis, the data in those axes and couple them together using the balanced photodiodes that can be canceled out any phase change that has been brought in because of the polarization change. And the other method that is being used is the digital signal processing, that can be able to be used, the software based that can be able to be used, that can help to be able to compensate for BMP at any particular moment. And actually, this is the method that is being used mostly at this time. Because the legacy generation modulation formats, you realize that have a lot of limitations because they are incoherent receivers, that you cannot be able to manipulate the phase of the data to be received and recognized. Network design and management, we can be able to build compensators. The way to join the fibers carefully, be able to join fibers carefully so that the coupling can be done and the less and the polarization coupling at the joining points can be able to reduce of power at the joining points. If it's reduced, we have managed the polarization dispersion at the end of it. Am I clear? I hope. The chromatic dispersion, thank you. The chromatic dispersion, what I've shown is the signature of chromatic dispersion. One is due to material, another one is the mixture of the dispersion due to material and the waveguide. When you look at it, the zero dispersion on the red one is exactly crossing at around 1310. And the first fibers longer distance was majorly being transmitted at 1310 because at that particular point, the dispersion is very low. At this particular moment, we moved on to 1550, and I will explain why. Because of it's easy to manage the attenuation due to APM-topped amplifiers that are key for improvement of power. So the dispersion is totally wavelength dependent and waveguide dependent and material dependent. If you can be able to manage the waveguide and manage the material that is being used to manufacture, and then you have managed the dispersion fully. Here I'm showing the different fibers that are being used at this particular time in space. And then I'm showing the chromatic dispersion versus wavelength. We see the traditional or standard mode fiber. When you look at it, the G6 fiber, G652 is the standard single mode fiber that has been used for a longer time. The other one, 653, it's called the low water peak. It has low absorption of water, particular wavelength, around 1400 nanometer. And they are very good for multi-coupling of wavelength, what we call dense wavelength division multiplexing. The other one is dispersion shifted fiber, 653. When you look at it, it has been shifted from 1550 and is going towards the 1600 window, the 1600 window. And when they manipulated the standard single mode fiber and shifted the dispersion, and then the dispersion reduced to minimum. When you look around 1650 or 1570, around there, you realize that the dispersion is very low. So the transmission can be done within that particular window. The other fiber we have is what we call the cut-off fiber, 654, G654, 1600. That one, 654 is not here. Is the non-zero dispersion. We can still have the dispersion. We can be able to move because we can be able to have the compensator, the dispersion compensator. And this type of fibers is called 6522. And it's also optimized for DWDM. The other fiber we have is what we call non-zero dispersion. 656, G656. It's optimized to operate at between 1300 to 1400 nanometer. And it's actually a wide band from 1460 to 16.5. You can be able to. When you look at it between the standard fiber and shifted, still has the low dispersion within it. The one is the bend insensitive single mode fiber, G657, and they are good for access. As I said, they have small radius bend to be used for access. Fiber to the hub without any big problem. The attenuation is another virus that we have in fiber. Beside dispersion, another virus we have, but a lesser virus, is attenuation. Attenuation, it reduces the power as signal snails through waveguide. And in that case, it causes sensitivity of the signal at the receiver end. Have different attenuations. So it is good to look at the specifications before you look at you buy the fiber or use it in that case for you to do the system implementation. Here we see the wavelength, the attenuation versus wavelength, and the attenuation is measured in terms of dp per kilometer, how much power is lost per kilometer as the signal is being transmitted. We still look at the 1310, our window 1310, you realize still is low. It's not as high as we think. But attenuation is high at the window of around 22 micrometer, which is 200 nanometer, and 1400 nanometer. And this one is just because of the OH elements. And these elements always absorb light. So if you can be able to reduce the OH elements in the fiber, and then you have reduced the attenuation. You remember we had the fiber called the low water peak fiber. It has been designed with low dispersions, attenuations at in this particular windows of 1200 and 1400. The transmission is at 1550 or 1310 at 15, realize high, we can be able to manage it because of the amplifier that was discovered in that of 1550. So here a diagram that indicates the radius of different fibers. Our standard single mode fiber, the radius is 30 millimeter. Radius bent, you can is millimeter. If you have to transmit light to a longer distance and maintain 0.2 dp per kilometer. The other one is we have the G57 A1, which has a bend radius of 10, But the lowest one is the one that many companies are using to lay fiber to the house. It has a bend radius of 5. It can be able to go through the corners that in our houses without problem. So please, as you look at the fibers, you also look at the bend radius, how much loss can you be able to attain, and how much dispersion can you be able to minimize for you to maximize the reach. The data can move, and for you to manage to maximize the speed of the data. We see here the diagram that shows different windows of transmission. We have different windows of transmission of signals through the waveguide. I know there is a first window that came at around 850 nanometer. That was the first that was discovered, and light was being moved through the waveguide but for very short, which followed closely with the window of 100, which we call the O window. The window between 1450 and around 1408 or 1475 towards this end. And in this window, we call it the E window. What type of we can be able to get in each and every window? Like we have the window of 1400, see the single mode fiber we have, because of the OH elements, we realize that the losses are very high. But the low water peak has been manufactured with low dispersion at this particular. The zero water, it has the lowest dispersion at that particular moment. And by the way, it can transmit data for a longer distance without amplification. The other window we have is around the window of around 1480 to 1520 or so. The window is called the S. The other one is the historical window that we have used to transmit the data, is called the C window. The C window. This one, the C band. This one is between 1520 and 1570 nanometer. And most of the fibers, when you look at it, it has low dispersion, low loss at a particular moment. Yes, some of them might have high dispersion at this particular band, but you realize that the losses are manageable. They are low enough. If you can be able to manage other losses from the splicing and the connections and the connectors, and then you can be able to transmit data for a longer distance at a higher speed. We have the L band that runs between 1570 up to around 1620. It has opened up a window for transmission of data. Realize that still low. U band of looking at the end. I move on now to touch on optical transmitters. The optical transmitters. It's important to understand how the signal is generated and how the signal is manipulated, how data is on the signal, which I always call a passenger vehicle carrier. A passenger vehicle carrier, the passenger is the data and the vehicle is the carries the over. Here I'm indicating, I'm putting through the system that we use to manipulate data at the input. Our laser or the light source. We have our light source. It can be a laser, or it can be an LED, or it can be an LED. And then we have the manipulation is done through what we call the modulators. The modulation is done in this particular system. So we have the modulator and we have the laser. Both of them need driven, and they are electrically driven. The laser it has a driver, and that driver can be the bias, and maybe you have to match also the temperature, because the lasers, most of them heat up so much. So it's good to control the temperatures so that you can be able to manage the line width. Cannot be the spectral lines at the end of it. And then we have the signal generator that can generate our data to be able to be manipulated, And then we have the driver to our modulator, which is the DC source. I'll tell on this manipulation of the time. When we have the data, and we have our vehicle, which is the laser, and the laser has been powered, and the modulator has been powered, means our waveguide is active, and then we can be able to make the data to be attached on the laser and can be able to come out as an optical data. What comes out, a manipulated data, manipulated signal, is an optical signal. That means we have a carrier and we have the passenger, which is the RF signal, if it is so, or random data bits like our voice and so on, that we can be able to move it through the system. So types of laser sources, there are different types of laser sources depending on coherency, depending LED has a larger broad line width. It can be able to have many spectral lines inside, many colors inside there. And that's why it's not easy to use it to move data for a longer distance, but it can be used for shorter reach systems. If you want to move it within a particular hub to hub, you still use the LED at that particular moment. We also have what we call the lasers developed out of the vapor period. We call it vapor period lasers. I know somebody must have touched this for the last 1 week or so about the vapor period lasers. And you realize that the line width is a bit, and it cannot be used a longer distance before the signal is passed because of the dispersed spectral lines. This that can be able to manage it. The LEDs for short distance, 1250 to 1350 is possible, or 850 nanometer is possible. The visible range is quite possible to use the LEDs. But the breakthrough came when we had the DFP, the distributed feedback laser, that has a very narrow line width. It can be so narrow, such a way that you can easily have one polarized light. We can have a single polarized in it. Remember the experiment we used to do, and then we measure the polarization of it. You realize how much you turn the polarizer, manipulate the polarization. It just changes in a small angle, but it cannot to the extent that it can be able to have a dispersion in the light. So the line width is very narrow, and this is majorly what we depend on for long distance transmission. We have other lasers that we have that have been manufactured and given breakthroughs to. In that case, this one is vertical cavity surface emitting. They're among the cheapest market and very key for short reach, short distance transfer. They are very key. In that case, the power output is low, yes. The power output, but if you are more distance, it can easily be managed without the line is a bit prudent, bigger than DFP, is enough to transmit data and be able to be used in any other applications, like in medical, in sensing, and other in agriculture. You can be able to see the VCSELs being. Carefully, please, I'm saying carefully, you should be able to choose the lessons carefully to minimize the dispersion, minimize the scattering, and increase the reach, the distance to move the data, and also increase the speed. Yeah. Another breakthrough that has been able to come in to make sure that we have the technology we have at this particular moment is the coherent sources. Coherence is because you want to have a particular phase and move with the same phase up to the end. So the phase change is constant over space and over time. And in this case, and then we have lesser high monochromaticity, high spatial coherence, high temporal coherence, high power, and ability to modulate. I move on now to look at the modulation. And the modulation, we have two types of modulation, one called direct modulation, and another one is called external modulation. We have various lasers that can be directly modulated and externally modulated. There are various schemes for modulation, for modulating the data. The first one is the traditional one where we understand that is called an off-keying, or OK, on-off-keying. It's majorly the intensity. We only be able to detect the intensity at the edge. So we just have the high power and the low intensity that we can be able to manipulate. Directly modulated and then externally modulated, the multi-level PAM, pulse amplitude modulation, that can be able to come in. Is what we call the phase modulation, and there are two types of phase modulation. We have the binary phase shift keying and the quadrature phase shift keying, which we can be able to look at the phase and be able to look at the same time. Be able to carry the data on the phase without any big problem. In that case, we manipulate the phase of the signal. The other one is polarization modulation. Modulation. This one, we manipulate the data on a particular polarization. As I said, it helps us look at the improvement of the dispersion by looking at the polarization diversity at the receiver end, by using the polarization, the beam combiners, polarization beam combiners, and the balanced photodiodes. The last one is the amplitude modulation, the dual polarization quadrature phase keying. This have come in key because can help us manipulate at the same time that we can be able to carry the data on intensity, and we can be able to carry the data on the phase. Be able to decode without much by coherent detectors at the end. Directive modulation, we can be able to look at, we can be able to say that the transfer be done good enough second until attains very high bit rate. External modulators, there are different external modulators. I can find it. We can be able to have our data, which is VT, and we can be able to have the biasing, which is our pi, as we manipulate it. The transfer function, it depends on this equation, where we can be able to see that it depends on the ratio of the RF signal and the biasing signal. The RF signal and the biasing signal. So the phi, in that case, what we call biasing voltage, it depends on the size of the waveguide, the interaction the interaction correction between the optical field and the electric field and the electric optic coefficient. Please, how is manipulated, the external manipulation, we can be able to use what we call the Mach sender. And in this case, we can be able to manipulate one arm as we keep the other arm constant. Or we can still have the voltage, the electric field manipulated on the two arms. And then we can be able to look at the phase components of the two, from the two arms, how they interfere, and then be able to change the back to intensity as it goes through. So we can be able to have the power ratio, the transfer curve, the transfer function is the power ratio as a function of the phase change. As a function of the phase change. So if we have, in case we understand and say, okay, let the phase on one arm be 0, and the phase now depends on the electric field on the of the Mach sender, and then is 0. Realize that you have maximum power. If the phase is pi over 2, and then you have the minimum power. And the phase is pi, and then you have the maximum power, but in the other phase. This is what I'm trying to explain, that if you have your phase change, minimum power is happening when you bias at pi, and maximum power will be able to be found when you bias at zero phase, or we bias at 2 pi. That one depends on the V in relative to V pi. The V pi can be constant, and as you vary the V, and then you come closer, or V pi. So the electric field, when we look at the electric field, the optical field, this is the optical field. The optical field will be able to give you a curve, a signal. The electric field point will give you a, because if we say the V pi is the VT is equals, the VT is 0. In this case, then we shall get that the maximum electric field will also happen next closer to the ratio of V pi, of V naught to V pi being high. But when VT is equal to biasing voltage, and then we to whereby the ratio of E to E naught is equals to 0. That one happens when at the point of pi. So if you draw the transfer curve, it will be able to look like this. Electrical part of it. The electrical part of it. So what happens with the data? When we want to modulate the data, we want to modulate the data on this particular, on this data. What do we do? We look and say, look at the quadrature. We look at the quadrature point. At this quadrature point, we'll be able to transfer the data very well. And remember, the data is from 0 to 1. And a 0 can be a 0 can be 5 volts in this case. Why? It can be the point where you have the pi. At this point you have the pi, we have the maximum transfer voltage, the maximum bias voltage at this particular point. And in that case, you can be able to find that you have a change of phase. The electric field has changed the phase and come down. So It's important to realize in modulation we take care of what we call the extinction ratio.
David?
The extinction ratio. Extinction ratio can be compared to visibility of interference fringe. Gives you what power can you be able to transmit out of the modulation, out of the modulator.
David, I think you can stop.
Polarization dependence.
David?
The modulated signal is polarization dependent,
David?
and is good to manipulate the light so that you can be able to couple maximum power into the modulator by
David? David?
optical receivers. Optical receivers
cannot
at
hear me?
the end that we can be able to use to with
David? Can you hear me? I'm sorry, can we have a break maybe for questions, if you don't mind?
It's okay.
So, from the audience, any question? Fibers? From the students, yes? There is one question.
Thank you, Dr. David, for that insightful presentation. I have a question on a specific amplification type called chapped pulse amplification. The other time when they were presenting on fiber lasers, they mentioned this amplification technique. So I just wanted to know, in a scenario where you have the VCSEL and optical fiber pair, is it recommended to use this amplification type maybe to extend the reach, considering the fact that VCSELs are generally susceptible to frequency chaps?
Yeah, thank you so much. Yes, we can still use. Can I answer, or is there another question?
You can
Can I answer?
Yes.
Hello. Okay. Yes, it is possible to use amplifier when you are transmitting using VCSEL. I'm going to show one of the papers that our group has published that has used VCSEL, and we have used amplification. Several transmissions we have done. We have used VCSEL in this lab, and we have several of them, and we use ABM. It's possible.
Okay. Any other question from the students? What about from the online? Okay, maybe I have a quick question as well, if possible. I was just wondering, how can you use these devices for other application as well, apart from communication? For example, for the Mach senders, is there any other application or that is not communication related? Oh no.
Yes, there are several applications. One of the applications we have is sensing. James is coming in with the sensing after me for a short while. We'll touch on sensing. We have also another application in medical. We can be able to very well, and we have also applications in agriculture, which we are dealing with in our lab in this place also, that we use lasers for. Yes, there are several applications, but because of time, I might not be able to most of them.
All right.
So we proceed.
David, there is another.
Okay, thank you, David. You talked about different types of dispersion which occur, that is the mature dispersion and the waveguide dispersion. And later on, you talked about the lasers being used to transmit the signal. And the laser beam may also cause distortion as a result of nonlinear effect like self-focusing or defocusing. How do you compensate distortions of the signal?
The compensation of the signal, they are mentioned, the one we can still use if you have a dispersion which has it's a positive coefficient, you can easily apply another fiber that has a negative coefficient just to slow the fast moving spectral lines and fast track the slow moving spectral lines. But we can also be able to use the digital, the algorithm. What do we call the digital signal processing at this particular moment? Most of the systems now are using DSP to compensate for the dispersion, and it's working very well.
So if there is no more question, we can proceed. Thank you, David, for answering.
Let me continue. I'm looking at the optical receivers. I'm going to move fast because I'm seeing my time is gone. The optical receivers is actually at the end of the system. We need to couple the light as well. We can have our signal out, and we use the photo detectors. In that case, come in handy. The photo detectors in this case will only be able to look at the intensity part of it. The intensity part of it. So there are different photo detectors. There's one which we call direct detection. And in the direct detection, we only look at the intensity for detection, and then we also what we call the receiver for binary frequency shift keying. At the end of it, we look at the frequency difference by decoupling using two photodiodes. The limitation with this is polarization part. In that case, the spectral efficiency is low. Then we also the high loss of phase information. This is what we call the hybrid, which is non-coherent and differentially coherent detection. We can be able to decouple using the polarization technique. The polarization technique. This one is the technology on the chip, which is coherent detection. We can coherently detect the light by using a reference called the log to compare of the input and the phase at the output. We use the phase difference to decouple the light out. How the QAM and K came in handy for us to use because of the discovery of the coherent detection. And we have the heterodyne and the homodyne detection. I pass on to passive optical networks. In passive optical networks is the technology that is still in the manufacturing process, but it's also being implemented at this particular moment and to access networks. Is used networks. It's majorly 90% passive. I'm just giving some of the experiments we have done in the lab to look at the pawn. We have a pawn at the end of it, but we generated the optical signal using comb technique, the comb technique, to measure the bit error rate at different split ratios. As I said, we have used pixel in our lab here several times. Lab here, and we particular moment used pixel to show that we can be able to manage to do the technology for 5G in combination with the, and we managed to come up with the analysis for BER versus the received power. Here we are showing that we have filtered out two spectral lines. One is carrying the data, another one we use it as a local oscillator. We use one as a local oscillator, and with the other one we use it to carry the data. We have also some applications in telescopes. We have being installed in various parts of African countries, and one of the countries is South Africa, at Cape Town and the Karoo, and we were laying the network in the telescopes, and we were able to the phase of the signals, be able to stabilize the phase of the signals. If we look at this, we can be able to see that you look at the phase of the signal, but if you can be able to stabilize it, it becomes constant. This one can be proved when you look at called the Allen deviation. Look at the Allen deviation, running one with control. You control, you realize that actually it becomes changing over. And that's when I come to of my presentation. My presentation, that is part of our collaborators from Africa that we work with. Thank you so much. So I will invite James to make a presentation of application in sensing. Please, the application in medical, but because of on wearables, be able to have the wearables that can be able to be sensed using optical fiber to be our take at this particular moment. Thank you. James?
Thank you, David. Good morning, everyone. Yes, can you hear me?
Yes.
Okay, I'm gonna just a moment, please. Okay, can you?
Yes, we can be able to see James.
All right, good morning once again to you all. Thank you for having me on this platform. I'll be looking at optical fiber sensors and applications, and in my talk, I'll just cover a few applications which we done and embarking on with the Center for Broadband Communication Group. So to begin with, of the concepts of optical fiber sensors is not different from applications or the concepts that are used in telecommunication networks. So basically, we are still using the same optical fiber. In some instances, the optical fiber is modified for specific reasons, maybe be they chemical sensing applications, or in other cases you would add some hygroscopic material to enhance the sensitivity towards moisture. So we know that the glass material is basically a core, the fiber material is basically a core made of glass, which has a higher refractive index than the cladding. And this is how we confine light by total internal reflection. But during communication, the idea of sending light from one end to the other is been seen to have some effects like attenuation and some effects which are like a polarization shift, or what we can call polarization fade. But for any perturbation or disturbance that happens onto the fiber along the way, it is actually picked as a kind of noise signal towards the end, which needs to be corrected for. But when it comes to of the sensing, because if we can get the effects of the noise signal that has been detected along on the other end, then which means we can be able to detect any disturbance along the signal and sensor. So in sensing, a basic sensing system will consist of elements which I've shown in the block diagram, where we have the basic sensing element which detects or picks the signal. We have the signal processing element, usually it, or signal conditioning element, usually that has changes the sensed signal into a format that is ready for processing. So most signal would most systems will also have the processing, where the signal is then processed to be ready for output. The fiber system is not really very different from it, because the sensing element and the processing element are all encompassed within the laser source, which is the laser interrogator, and the fiber itself. And it is important to note that the fiber in this case is both the sensing medium and the waveguide. So that is quite unique in application as compared to the conventional electronic sensors, if I can put it that way. Mechanical sensors, where you would have a sensing element separate from the transmission side, where you would transmit the signal in the form of a current or in the form of a voltage across conducting electrical wires. The part with the diagnosis system is usually that is by using a feedback system back to the laser to try and control the way in which the system operates. So that is mainly important when it comes to distributed fiber sensors, which is another area that I'm just gonna discuss in this talk. The output or the output end in fiber sensing consists mainly of a photodetector, and the photodetector is basically a photodiode which converts the optical signal into electrical signals, and then that makes part of the data acquisition, the sampling, and the analog to digital conversion is done. Comes the processing part, where we have the DSP algorithms that would run, and also that comes at the readable. So this block diagram again is an extension of the optic fiber sensor, where we see from an optical source, we have our light going into the fiber, but the light goes into the fiber, it will pass through a point where it is modulated, that is in the field. So it can, depending on what is to be measured, it could be temperature. Fiber can actually be able to measure vibrations. It can measure strain. or stress, which is a form of dynamic and static strain. We can also measure humidity with fiber sensors, depending on whether they're point sensors or distributed. So the different applications are unlimited. Voltage can also be measured, electromagnetic fields, and a lot more other applications. So we can different modes of operation of fiber, where the transmission mode is a transmission where the disturbance that is impeded onto the fiber is transmitted to the other end, and the data acquisition and signal processing is done from the far end. While a reflection mode uses a Rayleigh backscatter, which is also something that David touched on when he was looking at losses of absorption and what causes attenuation in the fiber. But in this case, some of these, like I've said, noise is basically part of what we are harnessing in terms of sense. And also Rayleigh backscatter in this case is harnessed or used to enable the reflection mode, where the Rayleigh backscatter is analyzed or is detected and analyzed to sensing at each point along the fiber, and this is of distributed fiber sensing. So when we look at the optical signal itself, it would consist of an amplitude term, consist of a field mode distribution term, which deals with the polarization. So the amplitude term is basically the first term, that is the magnitude or the intensity. And the field mode distribution term is one that relates into the polarization in which the wave is aligned. And we then have the phase term, and then spectral term, or the wave number term, that is which is the last part in this equation. So basically what carries or what is modulated within the fiber whenever is impeded. So when affected either by constricting the fiber or just by a vibration or anything that would simply couple into the fiber, it will affect one or all of these fields within the optical signal. So when that happens, we can have an intensity change, which is during constriction. The bending of a fiber reduces the intensity, so this amplitude term is affected. Or the polarization, which is random birefringence that we know is existent within the fiber. We can have the external perturbation, polarization state of the light and depict in polarimetric sensors. Then in monitoring phase, the phase can also change in the same sense, and any phase change by change for interferometric based sensors. And we have also some spectral based sensors which look at the change, the wavelength or in the wave number of the propagating wave as a result of the perturbation. This in fiber break gratings, which are also another kind of sensor that can be used either as a sensor or distributed sensing. So what I'm trying to demonstrate here how we use intensity-based sensors, and these intensity have their own advantages and disadvantages. The main advantage is that they're simple to construct, so that makes them cost-effective, but they have the great disadvantage of maintaining intensity, so quite poor sensitivity, and also inaccurate in measurement due to intensity fluctuations from source itself, and also background light coming from the surroundings. These can also be get rid of problems, especially to do with inaccuracies that come with fluctuation by making reference of different have a reference arm that contains the light that comes from the sensor and also the one that comes from the part. So the application for such kind of a sensor, if we look at the part in red, is in displacement measurement, such that if ever the back intensity, that will be detected at the photodiode. In this case, with a reference arm would show each time the intensity, because the intensity might not a reference comes from that particular laser, a direct measurement which shows a relative change between the intensity from the source. Top of the fiber in a way that will suppress pressure upon different parts of the fiber, and that will constrict the light that passes through and therefore impede on the intensity. And the amount of by which the intensity decreases, or the amount by which the intensity will vary, will therefore be a measure of how much pressure is being applied onto the fiber. The application of spectral based is with fiber break ratings. The operation of fiber break ratings is based on having a gratings inscribed within the core fiber, and the grating would be such that the of the variation of the refractive index of the, if made in such a way that the distance between is wavelength of the light that will be reflected by that grating. So the equation there was that the reflected wavelength by the spacing lines. So if the lines the lines of the gratings are made different or differently separated, would be able to reflect back different wavelengths. So if in this example, we've got lambda B1, different parts that is coupled into the fiber. We see that at the output is reflected first at lambda B1 by the fiber break rating 1. Then the yellow part is the second part, meaning the distance of separation is there, or the grating lines are separated to a distance which is of the blue wavelength, which is even shorter, means the break in that rating 3, and we can have as many break ratings, each with its individual thing to reflect a specific part of the wave that's passing through. So now the application for this in sensing would mean that if ever a strain is applied onto the fiber core, it tends to affect the spacing between the grating and to shift the wavelength that will be reflected back. And the wavelength shift can be used as a measure of the polarization-based sensors are mainly so very sensitive. I would say they actually compete in sensitivity with the phase-based sensors. Was polarization, when you look at polarization, mainly you're looking at the phase difference between the orthogonal components for the optical signal. One which we can consider them to be white one in the Y. So as long as they're in phase like they would do in free space, then the components have zero phase difference. But once they are coupled into fiber, which has a different optical density than that of X, we tend to see the components, the X and the Y components in the fast axis, other in the slow axis, they will be separated or they will disperse. Polarization mode dispersion in the process, and also due to random irregularities in the core of or in the waveguide because of irregularities that during the drawing of the fiber, you have that random difference, which also causes the polarization to shift in a random manner, meaning that these components, the X and the Y components, are also changing phase or being spread or separated in having a phase difference that varies randomly. But when it comes to the sensing part, the same applies. The moment a perturbation to the fiber tends to influence the shift in the phase between the orthogonal components, and that shift can be measured using using a polarimeter device, which is a polarization sensitive device that gives us the SOP, the light that's coupling back from the fiber. So in this diagram, I've to show a kind of measurement. We're using reflection, and this reflection is usually based on a backscatter, or if we have mirrors for a point sensor, then it will be based on Fresnel reflection from the end mirror. But in whichever case, the reflection will bring will bring back the phase detected changes that will be also the will also be detected by the polarimeter device and can be through a computer after processing. So in one of the applications, we've used such a setup in measuring or monitoring the structural health of a wind turbine. So in this case, we used a fiber, wound a fiber, the frame of a small wind turbine, as shown in this diagram, for this field test. And each time it's rotating, would also see the SOP, which is the state of polarization, through the stock oscillating at the same frequency as the turbine. So now structural health systems tend to be to head towards failure. The vibration changes, and you see a shift in the frequencies or an introduction of higher amplitudes and more spectral components. So in the process, when this happens, we can then be able to detect if a system is becoming unhealthy. So when a system becomes unhealthy, the measurement can be early warning metrics. The point show polarization as this is a sphere of unit radius that just shows the three Stokes parameters that would define the state of polarization of the optical signal that is being received. So whenever there is a perturbation on the fiber, we see a jump between certain points. If this is a periodic kind of perturbation, it was more different sphere. This is what then gives us, or what we can plot as a periodic time trace of polarization, also synchronous, or which is also in sense the same as the vibration that is emitted. In phase-based sense, the diagram that I also in the previous, this diagram has got an interference. This is basically one arrangements that we have designed and come up with the lab using fiber, where we have a splitter, which is basically a coupler turned around like this shift interferometer kind of setup. So this kind of setup, I'll talk more about it under the application, combining ferrometric setup for improved sensitivity and also monitoring polarization. So in phase-based sensors, like I said, the polarization are not very different. The only difference is that the phase of the polarization-based sensors is orthogonal for the orthogonal components. Otherwise, in phase-based sensors, we're mainly looking at the phase of the signal. By monitoring the phase, we can be able to also detect the different changes, be they dynamic or static within the system. In the to show here is basically part of a demodulation technique. The TDR system or distributed sensing system. So this is basically where one phase of a system is monitored, and an interferometric setup is used, in this case on the 3x3 coupler, where we have a Faraday mirrors on the within the micrometer setup. So different interferometric setups are used. Some systems interferometer setup that is usually for the forward propagating systems. So since we may use a single-ended monitoring system in our, we would basically use a system like this. We can have the back reflections and monitor everything from one end in in this case, as opposed to end-to-end monitoring, where you instruments on one for the other. So for this system, balanced photodiodes are used with 3 of them that are used. This system is actually sort of device intensive, but it makes it actually less computationally costly in the process. And this kind of receiver technique allows us to get rid of effects of polarization signal. So the balanced photodiodes 1, 2, and 3 will receive signals that are 120 degrees apart in terms of phase. So once they are in the dark, it means each time there is polarization fading, it is actually that polarization fading will not be the photodiodes that are still picking the signal with enough strength. And the difference between the path lengths on the Michelson interferometer simply will also determine the length of the signal, or let me say, of the in the system. It actually gives us what we call the gauge length, which is the distance within which the sensitivity can be done along the fiber. Advantage with fiber, other than I've talked of point sensors mainly, is that when we make distributed sensors, we tend to have every point along the fiber becoming a sensor. So from instead of having 1,000 sensors, if we want our sensors which are a meter apart over a kilometer, it means we need 1,000 electronic sensors. But if we have just a kilometer of fiber, it means the fiber, if it has a resolution of 1 meter, can simply give us the same 1,000 sensors without need for each component having its own electronics. So fiber, a distributed fiber, also bring some significant in that sense. So one of the applications that we have used, a sensor that we have designed measurement, precision measurement. We've managed to measure
James?
the dense.
James, sorry, I have to ask you to conclude. Maybe minutes, and then we have to move to the questions, if you don't mind.
All right, thank you for that. Okay, so I'll proceed. For this, we just were able to measure events that are within 0.1 microseconds, which is like a tenth of a microsecond with such a system. So it was just a simple experiment that we used by bouncing a ping pong ball on the table, and the fiber would pick the acoustic signals from a distance of more than a meter away. We were able to characterize this bouncing ball in terms of coefficient of restitution, the time of contact between the ball and the table, and all the like. It was actually quite fascinating to see how sensitive such a system is. So with the bounces occurring on such a surface, you can see this is when we compared the geophone that is used commercially in the field for seismic measurements and the fiber that we had developed within the lab. So the signals here, signal from the fiber is actually quite clean with a good signal to noise ratio and good. It doesn't have like some kind of damping problems in terms of recovering between sections. It was able to distinguish between very small bounces towards the end of the bouncing of the ball. So that was the major advantage with this system, and we could see how we could see like a better precision and better resolution in terms of measurement of successive events. Then this is the setup that we used, and we have this paper with the Optical Society of America, which is current Optica.
All right. Thank you very much, James.
In the other set of applications, we've made a distributed sensor which is designed to monitor sinkholes along in areas fiber is deployed. As you saw from David's first slide, where he was showing how the fiber networks across the continent run. We've got several millions of kilometers covered by fiber, and if we can use that fiber for distributed sensing, it means we've got a strong network of monitoring in or within our areas. So in application of distributed optical fiber, there are systems you can use. One can be based on Rayleigh scattering or Brillouin scattering. So the Rayleigh backscatter is what I've just been discussing all along, which is based on the size of which is 0.01% of the forward propagating signals. But even Brillouin is a result of between the forward propagating light and the acoustic waves within the waveguide. And depending on whether the acoustic wave is absorbed or generated, we get the stocks and the anti-stocks components, which are 11 gigahertz away from the central wavelength. Then the run is also a result of interaction with the vibration acoustic modes, molecular vibration acoustic modes of the system, and this is synced to 13.2 terahertz away from the central wavelength, and we use the in optical fiber. The systems I'm showing here is one designed in the lab to be based on polarization. So it's an OTDR principle, which where we send a pulse from the laser source, and that pulse it is all sent while it is moving towards the end. So that backscatter that is being sent, if we use time of calculation, we can tell the location at which the backscatter is coming from. And if ever there is a perturbation or impeding on fiber, then it comes along with the backscatter, and we can be able to measure both frequency and position and tell where any disturbance would occur within the system. Another system that we are dealing with, which is more...
James, I'm sorry, I have to stop you, if you don't mind. So I think for the sake of time, it's best now to ask if our students have any question.
All right, that's fine.
I'm sorry to interrupt you. So maybe just one question, and then we have to move on. Does anybody wants to ask anything to James? All right.
James, you can see in the chat the question.
The question says, based on fiber break rating and your work, how can optical sensors be made to give real-time stress and strain for undersea submersible structures to avoid accidents such as that of submersible? So it says Ocean Gate. So real-time monitoring, when it comes to stress and real-time monitoring, the whole system is mainly based upon the receiving or the detector part. So it's based upon the sampling. That is mainly what would limit or what would give strength to your system. So with the fiber break rating, remember you are looking at the back reflected signal, and when that back reflected signal, which is at a certain wavelength, is simply varying as opposed to the nominal one, which is known when the break rating has not been stressed. Then, which means generally just monitoring a real-time system will generally monitor the continuous variation. It will generally monitor that continuous variation in the signal that is being back reflected, and that can also enable real-time monitoring. But the speed with which, or the effectiveness with which that can be achieved is mainly based on, I would say, the sampling, the ability to quickly sample those signals. So it's something that's achievable, something that's doable. I don't know if I have answered your question.
I believe that yes, we can proceed. Thank you again to Jay for their talk, and proceed. Thank you.
Thank you.
So I leave the floor to.
Good morning. As you know, today is the International Day of Light, and we have to celebrate because we are using light in most of the activity. We are here more than 90%. We are using light, and then the president of the International Steering Committee, Dodel, some information that he very kindly sent to us. We'll discuss. It's mainly informative, and also we want to discuss with you. After this presentation, also read the message of UNESCO that we received yesterday. Harry will be with me here also in this activity. And we want everybody to give their opinion about the impact of light in your life, in your work, in your daily activity. Then will be something interactive, not only me speaking. Okay, as you can see here, today is the International Day of Life. We are presenting this activity here, but there are many activities taking place around the world today. We are some of them. This is the background about the International Day of Life. The first celebration in 2015 with more than 13,000 events in 147 countries, with a total audience of more than 100 million around the world. As an enduring follow-up, the UNESCO General Conference in 2017 declared the 16th of May as the International Day of Life, with the following goal. The first goal, to promote the importance of the science and application of life. Second one, to address challenges in sustainable development, health, and education. To explain the importance of science, education, and finally strengthen existing collaboration and stimulate new partnership. As you can read in 2024, the edition of the seventh celebration of the International Day of Life. This is perfect opportunity to review and activity. This is the topic of this year: life in our life, photonics technology, healthcare, imaging, art, culture, natural light, lighting, photosynthesis and light, light pollution, astronomy, light and color in nature. Here. Okay, a brief for the sixth edition of the International Year of Life since 2018. Okay, we have here in percent of participation, 68% is breakdown by event type: science, training conference, and online webinars. 12% all themed event, exhibition and festival. 5% event specifically targeted to school. 7% competition. 5% open days, citizen science. 2 global International Day of Life campaigns and shifted light and truth science. Now we have here the breakdown by United Nations regional groups. 10% event health worldwide. 3% in Africa. 22% in Asia Pacific. 8% in Eastern Europe. 80% in Latin America and Caribbean, and 39% in Western Europe, North America, and others. Of this, a total audience for 2023, 60,000 small events, and 550,000 global events and festivals. Total audience since 2018 to 23, 350,000 in small events, and 2 million global events and festivals. Okay, why the International Day of Life was specifically used to 16th of May? Because of the creation of the first laser or maser, ammoniac maser by Ted Hyman, as you can see here. He reported the first oscillation of the ammoniac molecule, and this is why the 16th of May was selected as the International Day of Light. Okay. As we mentioned, it will be dedicated to light in our life. And I am going back. Okay. These are the events in previous years. As you can see here, in 2021, the topic was truth science. During the 2020 and 2021, we ran social media campaigns. This had been planned in any case in great help and maintaining visibility during the pandemic, during the COVID pandemic. The 2021 campaign focused on design has become a partisan political issue. So our aim was to promote discussion within the photonics community, support Nobel laureates and others major prize winners, science communicators, science advocates, etc., led to more than 500 signatures, led also to political visibility. Activity during the next year were focused on, for example, in 2000 or future by IPs, Optica, and SPI. Also the ancient Nobel Prize Centenary, 75 years of synchro science, lighting the Charles Bridge in Prague and in Ukraine colors, Optica Foundation 20 anniversary, James Webb Space Telescope activities, total lunar eclipse, 16th of May, 22. And in 2023, the topic was focused on possible, also mainly hosted by the Optica, and were mainly light pyramid associated with COP7, AU, DAR, and Quiet Sky Survey, International Year of Basic Science for Sustainable Development, LUC, the Future of Urban Lighting, Gdansk Festival of Light, $1 glasses, and Good Vision. Daylight, as you can see there. And a regular promotion of different partners around the world. As you can see there, we had in read now you have it from there. Optical, head, and affordable air glasses. This was in the of Egypt, around the world, the celebration. Here I have, I cannot read very well.
Women and Girls Daylight Talk Series 2023. Student branches of the Chinese Optical mobilized for International Light 2023.
Okay, these were the activities around the world. And this activity were supported, of course, by the UNESCO and the steering committee. The steering committee, in this steering committee, we have all these organizations. As you can see there, we have also ICTP, you have the International Commission for Optics, the SPIE, Optica, and so on and so forth. Now, I apologize because the letter was so small that I couldn't read. Now I invite to Harry to read the message of UNESCO.
Yeah, as Jared comes, maybe we, as we UNESCO, let's come over. Let's be outstanding.
So thank you. On behalf of the Organizing Committee, to bring the message from Ms. Adre Asolai, the Director General of UNESCO International, 16th May 2024. We stand at a critical turning point. It requires us to think our relationship with the living world. In our consideration, it is crucial that we remember all living creatures, whether humans, animals, plants, or bacteria, rely on one basic source of light. The International Day of Light celebrates the technological, physical, and artistic uses of light and aims to promote a understanding of it. Without light, our planet will be but a cold and barren place. Where there is light, light represents humanity. And we need to observe this working together, fundamental structure, environment, and academic. Since ultimate frontier as a our landscape.
That basically is something that in high school, taking pictures. So my bachelor, then my master in. So light is, and I would like to.
As the first in my interest in light started way early when I was a graduate student, and I got to do research regarding interacts with matter. And for instance, when you consider light matter interaction, and when you consider specifically lasers for that matter, and most recently, for instance, one of the materials which have become interest to scientists is perovskite materials, which can be used to harness the solar radiation and therefore be used as solar materials, as solar panels. And I got fascinated with that area. And in fact, my research was on nonlinear optical properties of these emerging perovskite solar cell materials and how they interact. We know that they are very good absorbers of light within the optical range that is required for solar cells, and that will impact heavily, like in Africa, when it comes to harnessing of energy and how it can be able to transform our society so that we do not necessarily rely on the national grid, but more so we can be able to harness the solar energy. So for me, photonics has been great, and I've also wanted to understand the science, not just from the linear aspect, but also from the nonlinear. Thank you so much.
I want to invite one our student, Isma. Come here, here. You are very good speaker. Yes.
So everybody is with me. So for me, light is a very important technology because without light, we are not able to explore or basically light is a light with the research of light, especially education, like email. So good opportunities. May, they are for science education, technology to the whole community, and maybe and this is the purpose of my maybe you can say the whole life, to promote education community. People are not able to get the education, and I would promote the females where not able to get education. Education special. So if you bodies people make our life for me the
because that
that people know masters in this light can so many problems in this world. For instance, my focus area is on using light to solve medical problems. For instance, when I was presenting my poster, you saw how we tried to detect different in in rats, which can be translated in beings. So can be used to solve so many problems in this world, including now the medical problems, which is, for instance, you can use light to detect or for early detection and so many other applications. So I think light is a very, very powerful thing we have in this world.
I would want to take this chance just to welcome one of United Nations agency body, which is, I hope all of you know it, UNICEF is the agency like, and I'd like to welcome Madam Naila just to come and make to us as you join our workshop this morning, kindly.
Hello, everyone. Now I feel how it. Now I know how it feels to be put on the spot. So I was supposed to be a visitor and support a team that has come from very far here to celebrate this amazing concept. I had not imagined ever that I'll be part of such an occasion. So thank you very much. My name is Naila, and I am an educator by profession, and at the moment I'm running a project that is very much in line with what you're celebrating here today. We're looking at education as a tool for our community. My colleague said here, the development, we're looking at increase the rates of education in countries, especially knowing particular component of our universe, light, not as just being like that we are in an equator country where light is like, very easy. Of the daylight is even enhanced all the time and all. But yes, it is indeed a tool that for us educators, when we go their organizations actually working hand in hand with educators, teachers, to provide them with rechargeable, portable, tablets and computers, and that they can use to get education as well, because there are areas where there is no approach, like people cannot education or can have access to that. So indeed, I use, I'm here as a user of light, not like, somebody who is doing any research on it, but I know how important it is for us to make this particular component available for the people easily as we living in the developed or comparatively developed cities and developed towns and developed countries. So I'm very, very happy that somebody is actually enhancing the importance of it, making it, making people aware of the importance of it, and celebrating a day and celebrating this kind of knowledge and component of our universe. So thank you very, very much for allowing me to come here and and I really appreciate the work that you guys are doing wherever you have come. A very, very informative session. Thank you very much for that. I'm really honored to be part of this. Thank you very much.
Yeah, thank you, Naila. You are indeed not only an educationist, but being part of this workshop, you are also a scientist. And for your information, as Multimedia University of Kenya and even our other local universities, we are closing the door for the former 844 system. So we are going to the CBC and educationists. We shall need you because we are now changing our syllabus to actually conform to the new syllabus. And in the next few years, of course, even our syllabus, be it the BSc, BSc Applied Optics and Lasers, we are going to actually restructure it to conform with the dynamics of the world. And to the participants, UNICEF being a humanitarian kind of agency, this is also another opportunity to interact with our participants. Most of them, or some of them, are educationists, working maybe with universities or maybe high schools. You can actually link them up to some of the opportunities away from just the science or the lab, because we need to have a tie or a link between what we do in the lab and also what is in the society. So with those closing remarks by Naila, we go for maybe a cup of tea for the poster sessions. Thank you.
Humans have always been curious. Why the way it is? How does the world work? What does the future hold? The excitement of new ideas, the pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, everyone speaks one common language: science. Basic and applied research are both vital for society, from fundamental particles to black holes, from climate change to coding. Work at ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The exchanges and global scientific network built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding minds explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
We are all looking for something. Some of us search for a treasure, and some are looking for that which can only be found in our museum. Welcome to the Multimedia University of Kenya ICT Museum. Scan globally. Visit the main campus and be taken through the telecommunication evolution. For more information, visit our website at museum.mmu.ac.ke. MMU Museum, where the past meets the future.
Humans have always been curious. Why is the world the way it is? How does the world work? What does the future hold? The excitement of new ideas, passionate pursuit of new knowledge, expanding the horizons of all. These belong to everyone. The Abdus Salam International Center for Theoretical Physics has a unique mission that supports research excellence in physics and mathematics and the nurturing of sustainable science for all. ICTP's founder, the Nobel laureate Abdus Salam, believed that science is the common heritage of all humanity. The center supports researchers from less advantaged countries and works to remove barriers they may face. Here, Science. Basic and applied research are both vital for society. Fundamental particles to black holes, from climate change to quantum. ICTP is guided by curiosity and big ideas. ICTP's vibrant atmosphere of collaboration opens doors. The experience built here create fertile ground for new discoveries. These connections encourage brain gain. ICTP's training and education programs support scientists throughout their careers. They share their knowledge with students, enriching the global community of researchers. ICTP, where outstanding scientists explore the frontiers of knowledge, build capacity, and promote bright minds. A community united by the power of science.
Welcome to Multimedia University of Kenya, a center of excellence in engineering, ICT, and business studies. This is the iMac Lab that offers editing skills and use of iMac computers with various video editing softwares such as Final Cut and many more. This is our engineering lab, where we conduct technical evaluation of hardware equipment and software troubleshooting and fixing every possible technical issues. This is our physics and chemistry lab, where most practicals happen, including tests on materials and present research findings to scientists, ensuring safety and quality standards are met.
This is a computer lab, also known as Korea lab. This is where computer classes take place and most of the computers are installed with the internet.
our Laser and Optics Lab, which deals with laser and optics, including transmitting and manipulating laser beams or any other forms of laser light. Welcome to our radio. We have our own station that provides information to the citizens and people at Gatarongai. Listen to the sweetness of our radio on 99.9 FM and learn more from our students as they bring to you radio has helped students acquire communication skills in readiness to join national and international radio stations.
A laptop is an essential asset in the modern society. However, many of them are lost as a result of theft taking with them vital information. But now comes Electracker, an online system that gives users the ability to register various electronic devices using their serial numbers. To access Electracker services, visit the website, create an account, log into your account, register the device serial number. In case your device is stolen, you report in the portal. The tracker will then help you track and recover the device.
I had lost my laptop, but thanks to Electracker, I found it. Asante sana Electracker.
Electracker helped me track and recover my lost laptop. Wewe pia jaribu Electracker, cause iko fiti.
Greetings from Multimedia University of Kenya, National Institute for Optics and Lasers. My name is Professor Geoffrey Kihara Roremo. I'm a professor of lasers. I am going to give you an overview about the University of Kenya and also some very important information about the National Institute of Optics and Lasers, which is going to host the East School. Multimedia University of Kenya was established in the year 2013 after getting the charter from the then President of the nation. At the moment, the university has 6 faculties, and these are the Faculty of Science and Technology, Faculty of Faculty of Business and Economics, Faculty of Media and Communication, Faculty of Social Sciences, Faculty of Computer Science and Information Technology, and also an institute, which is the National Institute for Optics and Lasers. I'm going to give a bit more information about the Institute for Optics and Lasers, which was established in the year 2019. At the moment, the institute offers 2 programs, Master of Science in Applied Optics and Masters of Science in Technology. This is the only institute of its kind in Kenya and also in East and Central Africa. At the moment, the institute has a population of 30 students who are in different levels. Some are currently doing research and others are going on with their coursework. At the National Institute for Optics and Lasers, we are having quite a range of, and we are going to explain all this during the summer school, the East African Summer School of Optics and Lasers. We are going to give the participants a good overview about the kind of research that we are doing. So I would like to welcome all of you to come and attend the summer school, and indeed you are going to benefit a lot as you get exposed to the current research activities that are happening at the global arena. You are most welcome, and see you at Multimedia University of Kenya between 6th of and 17th of May. Thank you.
what we are having today is an ongoing training, ongoing from Monday. It's going to be 5 days until Friday, and mainly what we are training people in is the installation of solar. Every components from home. If anyone needs solar PV technologies, the panels, the batteries, the charge controllers, the inverters, and so forth. So from this training, the students that you are in the back view are very basics to from electricity, these components, what they entail, what are they going to look for when they go to purchase items, or even purchase, what do they need to from the place that they install them into. We are an avenue of creating job opportunities for the youth that take part in this trade, because now they'll go forth with the certifications they acquire licensing to be able to install these technologies as technicians.
This week we have a solar PV training, solar photovoltaics training. It has started from November. It's ending on 4th of December. Basically, we are instilling skills on solar installations, designing. We have participants, most are students from Multimedia University of Kenya, and they are really to know more about green energy technologies and solar technologies. After this training, they will be now skilled solar technicians.
I'm a third year student pursuing a bachelor's in technology. So this week we've been here in the T1, T2 training, which is a renewable energy research consortium. I'm going to be a participant. I'm here because I want to be impacted in my knowledge. At the end of this course, I expect to be able to be consulted according to the solar PV installation, and I expect to have knowledge installing myself and even assembling and coming up with new ideas in the world in terms of energy, concentrating on the renewable energy. So far is very good. It's the third day, but I have more knowledge than I expected. Right now we are doing the hands-on, the practical unit, and I think they are impacting very well because it's easier to understand when it comes to the practications more than the theoretic. And I think it is very beneficial to me so far.
The is good so far. At the end of this program, I expect to have gained more knowledge to be able to learn how to install, how to use the demands. The experience has been very inspiring, being that there are more female students than it's actually a great honor.
Was established, and it has been a continuous learning process. When I see carrying an overall, when I see myself carrying a solar panel, when I see myself connecting a battery to power the loads, it has been a wonderful experience being part of the consortium. We are more happy to have be training in new. It has been a wonderful journey since the consortium was born, and as you can see the growth, even having the first T1, T2 training, it has been a great milestone. It has been a wonderful reception, and the students getting to understand. I'd like to urge those in the science and engineering courses to blood up these trainings, mostly from MMU or rather any other institution, from any other company sector. They can come to obtain with the trainings that we have.
This week is a last because having the first T1, T2 workshop, whereby we are focusing on our young youth good feedback, whereby we have a total of 16 young men and women who are joined us in this workshop. We expect them at the end of the workshop to actually just apply what they have learned, and of course get licenses from the energy sector. At the same time, we are also working in partnership with the educational institutions in Germany, whereby we are collaborating into this hands-on. And I want to welcome all of you, especially those who are in the energy sector, to join us, be part of this consortium. The main aim is to actually equip the hands-on skills to these young, consultants. One of the skills is the sizing, how they are going to size these solar components. As you are aware, we have had a challenge in domestic and industrial sector. At the same time, once they get licensed, we expect that as a university, we are going to actually do a pilot project of a solar PV plant within our institution, and also awareness workshops within our community, just to make sure that we do actually the correct sizing of these solar components within our nation.
This is an adaptive optics kit, and in this kit there are a number of functions that can be done with it, and it's important to note that most recently, due to its advancement in the sophistication and the simplicity, so researchers have utilized these systems to make breakthroughs in areas of femtosecond pulse microscopy. We have laser communication, we have vision correction, and also retinal imaging. Although these are dramatically different fields, they all benefit from a simple experiment or a simple structure like this, the adaptive optics. And it's formed in three. We have three parts of this. We have the Schack-Hartmann wavefront sensor, we have the deformable mirror, and the control software, and that makes the first type of this.
Whatever is before you, Nicholson interferometer.
And one of the applications of Michelson interferometer is that it measures the thermal expansion coefficient. So in this case, we're going to thermal expansion coefficient of an aluminium rod that's connected to a banana plug. So when you connect the rod, as you can see, we have a digital thermometer, and the wires are connected to the IC regulated power supply. So when the voltage is adjusted to like a certain voltage, probably 5 to like 10, you notice that there are some fringes that are going to be produced there. This is because an increase in the voltage is going to induce a temperature change there. The temperature change will lead to an expansion of the rod. It's going to shift the mirror. The mirror, when it's shifted, you be transition in just
This is a Michelson interferometer, but we are using a different laser here. This is a helium neon laser. For a helium neon laser, it's not collimated and it has to be filtered. So that's why we have this lens. It's a convex lens. And then we have an iris that is having a hole, and we have another convex lens. So when the beam is coming, the second convex lens is already collimated. Then from there, we introduce a beam splitter, this one, that is going to split the light into two, 50-50 beam splitter, so that we can have the other beam path to form the interferometer. So this is a mirror, then this is another mirror. That's where we'll observe the fringes on the screen. Ideally, what I want to do, I'm going to replace one of the mirrors with my sample, investigating the effects of stress on the infants using the interferometry setup. So the first step is forming this interferometry setup, and then I'm going to be varying temperatures of the thin films and the humidity at different times. And then I'll be observing on my fringes, which I will connect to a CCD camera and a computer, and observe the way the fringes will be changing. From there I can use calculations to find stress, and then we'll be able to find how the thin films are going to be affected. So basically that's what I'm doing here. Yes.
Setup, and it consists of an LED light source, then condenser lenses, followed by a collimator lens, which collimates lights to the sun. Then once light passes through the second collimator lens, which collimates lens into the prism, and then the prism split the white LED into 7 constituent colors.
Yes.
This is an adaptive optics kit, and in this kit there are a number of functions that can be, and it's important to note that most recently, due to its advancement in the sophistication and the simplicity, so researchers have utilized these systems to make breakthroughs in areas of femtosecond pulse shaping. We have microscopy, we have laser communication, we have vision correction, and also retinal imaging. Although these are dramatically different fields, they all benefit from a simple experiment or a simple structure like this, the adaptive optics kit. And it's formed in three. We have three parts of this. We have the Shark-Hartmann wavefront sensor, we have the deformable mirror, and the control software for this purpose. Makes the first type of this.
is before you is Michelson interferometer, and one of the applications of Michelson interferometer is that it measures the thermal expansion coefficient. So in this case, we're going to measure the thermal expansion coefficient of an aluminium rod that's connected to a banana plug. So when you connect the rod, as you can see, we have a digital thermometer, and the wires are connected to the IC regulated power supply. So is adjusted to like a certain voltage, probably 5 to like 10. You notice that there are some free to be produced there. This is because an increase in the voltage is going to induce a temperature change here. The temperature change will lead to an expansion of the rod. So when the rod expands, it's going to shift the mirror. The mirror, when it's shifted, you notice that there are going to be transition in the number of fringes.
This is a Michelson interferometer, but we are using a different laser here. This is a helium neon laser. For a helium neon laser, it's not yet emitted, and it has to be filtered. So that's why we have this lens. It's a convex lens. And then we have an iris that is on the purpose pinhole, and we have another convex lens. So when the beam is coming from the second convex lens, it's already collimated. Then from there, we introduce a beam splitter, this one, that is going to split the light into two, 50-50 beam splitter, so that we can have the other beam path to form the interferometer. So this is a mirror, then this is another mirror. That's where we'll observe the fringes on the screen. Ideally, what I want to do, this is a setup that I will use in my project, but I'm going to replace one of the mirrors with my sample. I'm investigating the effects of stress on thin films using the interferometry setup. So the first step is this interferometry setup. And then I'm going to be varying temperatures of the thin films and the humidity at different times. And then I'll be observing which I will connect to a CCD camera and a computer and observe the changes will be changing. From there, I can use calculations to find stress, and then we'll be able to find how the thin films are going to be affected. So basically, that's what I'm doing here. Yes.
Spectrometer setup, and it consists of an LED light source, then two condenser lenses, followed by a meta lens, which collimates light to the slit. And once the light passes through the slit, it passes through the second collimator lens, which collimates lens into the prism, and then the prism split the white LED into 7 constituent colors.
Light sheet, something that you want is to be able to control the dimension of your beam. The reason is that, I don't know if you remember, but I mentioned the fact that it is important to control the thickness of the sheet, because if you have a light sheet that is thick, then you will excite the flow layer. You don't have a good axial resolution. If I can, but if the light sheet is thick, you have a long length, which means that your light sheet will be homogeneous in space. So it depends. Very thin light sheet and a very short Rayleigh length, because maybe your sample is small. Other times you prefer to have a wider, longer, let's say, light sheet and a thicker one. But to be able to change that, well, we can either a large, and indeed that will give us more focusing effect, or we can have a smaller light sheet and then the focusing of this beam, a smaller beam, and then the focusing, the capability of a lens for focusing it will be reduced. So we will have a thicker light sheet and a longer one. So I want to expand the beam. That's what I want to do. So that then I can play with it and I can make it smaller or leave it untouched, depending on what I want to do. How do I do that? Here I have the first lens that is, this is a 53 millimeters lens, 53 millimeter focal length lens. So what does it do? It focuses the beam in one dot, okay? In one very small dot. This is the focal plane, more or less. It's here. Can you see that it's focusing? Okay, so this is what a lens does. And then after the focus, it becomes larger again. Okay? It becomes larger, larger and larger, and it is divergent. If I place the second lens at a distance from the focus of the first lens that is equal to its focal length, which means the distance between the two lenses is equal to the sum of their focal lengths. Okay, what it happens that after the two lenses, my beam is collimated again, and it is expanded. Yeah. Right? Let's see. Let's try to still. It's 9 meters. Yes. Okay. So it's 4.5 more or less, a little bit less maybe. Okay. So there is nothing much very really special in what I've shown to you now. I mentioned the fact that here at the focal plane, in between the two lenses, at the focal plane from this lens, we have a Fourier plane. The focal plane is a Fourier plane. If I wanted to do some spatial filtering, I would do it here. Can I do something here? Yes, I could. For example, let's see if it is still well aligned. Elvis aligned it. Let's see if it's still. Well, maybe you can see it here. But if you come and you look from here as well. Okay, so this is the beam, the one that we've been talking about, and I would like to select, for example, if I want to select only the central spot, I can put here another pinhole that will reject all the other frequencies, all the ones that are around, all those rings, for example. After this, I have something that is quite nice. I think some of you might have already seen it because I've shown this the other day. Anyway, so this is a cylindrical lens. It is a lens that has, it's basically like a cylinder that was cut. It has, it's not spherical. You can already imagine if it has a curvature that is one direction, it will focus only in one direction. So if this focuses only in one direction, we can create a blade of light, right? So I can show you. I will put it here in front of, in the middle of.
Hello. Great stuff. Welcome back, everyone, for poster session. So let me introduce the speaker we have with us. His name is Dr. Zubair from Information Technology University. He's an associate professor and currently associated with as a senior research scientist from King Abdullah University of Science and Technology. So this is a kind of last lecture in our series, as I have mentioned several times during the sessions and all that, that doing for this design and simulation, you need the computational physics. So this lecture will be covering those computational methods like FTTD, details of those methods, and I hope it will be quite insightful for all of you. So Dr. Zubair has a vast experience in terms of developing such computational tools, doing all these modeling and simulation, as well as his core area includes bioimaging and biosensing. So with this, I will give an opportunity to Dr. Zubair. Please continue. So formation will be exactly same, that he will be speaking for roughly 50 minutes or so, and then there will be Q&A followed by the second lecture, and then 5 minutes, 5 to 10 minutes for Q&A. Yeah, over to you, Dr.
ICT for this invitation to speak at this summer school at Multimedia University. I'm also thankful to Multimedia University for such a nice arrangement, and especially to other partners, including UNESCO and UNICEF, and for this nice presentation of this school in a period which aligns nicely with International Day of Light also. So this is all commendable. Starting with the talk, Okay. So starting with the talk, the topic of my today's talk will be, as Professor Qasim mentioned, is about computational methods in electromagnetics and photonics. And so just a bit about myself. I am from Information Technology University. I'm associate professor there, and currently I'm visiting King Abdullah University in Saudi Arabia. And also I'm a visiting research fellow at University of Glasgow in UK. So in today's talk, what we want to introduce is to a more broader audience, where I was told there are students and more early stage researchers. So we would like to introduce a bit about computational aspects of electromagnetics and photonics, and some of the conventional techniques which are continuing to be useful in electromagnetics and photonics in general, and then some extensions of these techniques which are more novel and which can include some of the analytical methods from the mathematical point of view. In this case, that is fractional calculus, and some of the recent applications of these hybrid techniques which we have pursued in recent years. So we thought it would be a better idea to introduce some of these additional topics which may create interest in some of earlier researchers for some of the research problems which could be of interest. So moving forward, I will not spend too much time here. So this is just a quick intro of Innovative Systems and Solutions Lab, where I'm affiliated at ITU. It's a cluster of various labs doing a wide spectrum of research. One of those is Micro Nano Lab, where we focus more towards light and its manipulation. But here, when we say light, for the purpose of this presentation, light can cover a wide range of electromagnetic spectrum, which includes visible as well as non-visible regime. And when we say non-visible, it may include high frequency and low frequency, both regimes. So, however, for the purpose of computation of the problems which relate to either optics in the visible domain or any other electromagnetic wave which can be viewed or cannot be viewed, in all these cases, we can say that we are all speaking the same language as Maxwell equations. And the computational aspects of Maxwell equations are quite scalable, and they can be applied to domains which include even the frequency, microwaves, leading to infrared, and regime, which usually refer to as light. But for the purpose of this presentation, we can say that light here means whole of this electromagnetic spectrum. Innovative Systems and Solutions Labs, because we deal with almost whole of this spectrum. So there is a strong requirement of computational capabilities at all these frequencies, and my group at ITU provides that support. So I'm sure Professor Qasim in his lectures has gone through details of other activities of the lab, so I will skip this part. And I will just comment one thing, that an inevitable part of applied science and engineering includes at least 3 steps, and which starts from device design and optimization. Step that requires knowledge of theory, that particular device in that particular frequency or wavelength regime, and once you have that theoretical knowledge, you need to simulate, or you need to do, let me say, computational design of that particular device using some analytical method, which is possible, or use some computational tool. That computational tool can be your own code, which you have written based on the theoretical knowledge you have, combined with numerical analysis techniques. Or in these days, there are commercial tools available for various kind of devices in various frequency and wavelength regimes. So we will come back to that. So because most of our work requires the design aspect of the devices, so in our lab we have a computational design capability which is both in-house, and also some of it relies on the commercial tools. So in today's presentation, I will try to show some examples of the in-house capabilities, how we evolved them historically, and how they are proving to be useful in some of the cutting-edge problems. The second part in any of the applied work which we do here requires fabrication, and that fabrication can be at macro scale for the devices in the electronic or micro regime. However, because here we are concerned a little bit more on the photonics side, so it requires nanofabrication. So we have developed very meaningful collaborations with universities in the developed world, or the organizations in the developed world, where we regularly visit, or our students regularly visit there, or their students, they work on collaborative projects with us, and they provide a very much needed fabrication support. And the final step in the overall design process is the characterization and applications. So on this part, what we do in our lab is we have some local capabilities for characterization and testing. So the applications where the design knowledge is required in hand for the person who is doing the characterization itself, we do it locally, or in other cases, develop some meaningful with external collaborators. And ICTP recently, and several of our students have visited, or hopefully in the future will be visiting and taking benefit state-of-the-art labs at ICTP in Dresden to do the characterization of the devices they have designed back in home. So in this school, there have been few other talks, so they are related to some of this work. So I just want to just reiterate. So this lecture is part of the series. So here we will be dealing more in the first part of this lecture more towards the introduction of computational electromagnetics for early stage researcher audience specifically. So as I said, so before I move further, as I said, I want to reiterate for the student audience here that electromagnetic spectrum as a whole, for purpose of this presentation, call it light also. So some of this light is visible and some is invisible. So the visible light we can see is somewhere here, and here in this pictorial description, it shows the frequency and the wavelength region. And then if you go on the left, the wavelength is increasing, meaning frequency decreases. And if you go on the right, frequency increases and wavelength decreases. So on this slide, I want to show one more is very important with the computational aspects or computational point of view is that you will see in the third or fourth row this approximate scale of wavelength. Meaning, if you come into infrared and visible regime, the wavelength of light, you can see it's comparable to a needle point. It's very small, or let's say some protozoans. Or if you go to the ultraviolet regime, for example, the wavelength of the electromagnetic wave, same in as molecules, and if you go to the X-ray, it's comparable to the size of an atom, which is in some angstrom. However, to the left, the same electromagnetic wave will have which will be comparable to the sizes of, for example, of humans when it goes to radio frequency or even buildings. So we want to simulate the behavior of an electromagnetic wave in any of this scale. One thing which matters a lot is that how does that wavelength compare with the scale at which we want to simulate? So I hope my slide is visible, this electromagnetic spectrum. Okay. Can you confirm? I'm feeling there is some delay, or is it fine? I should continue. Okay. I can see the message. Go ahead. Okay. Thank you. So as I was saying, so when we want to simulate any problem related to electromagnetic wave, in this case, you can say light, or in the case of optical device or photonic device, one thing which is important, and I want to focus here, is the wavelength, how that wavelength compares with the size of the problem. Now, for example, we want to simulate visible light. So visible light has wavelength which is and if you want to simulate behavior of visible in a nanoscale, for example, there is a material which is at nanoscale, the device is nano size. Let's assume it's a graphene sheet. Certain carbon atoms arranged in a certain pattern, but the overall size of that thin film, you want to see the interaction of light with that thin film. The thickness of that film is, let's say, just in case of graphene, is thickness. It's atomic. It's compared to size of an atom. Now, in this case, the light has wavelength in the numbers of nanometers, and the thickness of the sheet you want to simulate in the vertical direction is in atomic size. Atomic size is somewhere in angstrom. So in this case, your wavelength is bigger than the direction at which you want to simulate the behavior of that light. However, so in this case, the problem is wavelength. So in this case, if we go to there will be complexity in the computation, but if we go to the size of the simulation problem, that simulation problem as a whole, in terms of numerics, is a sub-wavelength problem. In some cases, to simulate visible light on some molecular, at the scale of some molecule size or even higher, or let's say to the size of needle, let's say optical fiber. Now, optical fiber has a diameter which is still comparable or a bit larger than the wavelength of the light you are simulating. So now we are moving wavelength versus the size of the problem. And I will show later that wavelength versus size of the problem will make a huge difference when we simulate it. So if the problem is bigger in terms of wavelength, for example, you want to simulate visible light, how the visible light propagates through the human body. Now, the difference in scale is several orders. It's maybe more than 6, 7 orders. In this case, is 6, 7 orders higher than the wavelength. So the computation time and the effort we will spend, the size of the problem will be much bigger. So we have to be careful at that time that whether it is possible to simulate the behavior of light and its propagation through some human tissue, for example, or a human body, how much time that will take and how much computational resources we need that, because now it's a large-scale problem, etc., etc. So I will come back to this point, but just to give you an idea, wavelength versus the size of the problem is one thing we will keep in mind. However, in all these cases, we will be simulating Maxwell equations. And I will come to that. There will be one other factor which will be important. You will see here the temperature of the object at which these electromagnetic waves can create effect on the matter on which we want to simulate the effects of electromagnetic waves. So in most of the cases, we rely only on the Maxwell physics. We say we will only simulate how electromagnetic wave impinges on certain matter, and then whether it will be reflected or it will get scattered, or in some cases it will get absorbed. And when it gets absorbed or it creates something, let's say, more, there will be some other physics which is invoked at that point. That can be thermal physics, that can be some other aspects. So for the sake of this discussion, we will not go into multiphysics. We are relying only on the electromagnetic physics side. So, basic question: we know electromagnetics. We know that there is known Maxwell theory, Maxwell equations, which deal with the behavior of electromagnetic any material of our choice. However, why do we need a different area or a different specialty known as computational electromagnetics in this case? So to answer this question, the analytical solutions of Maxwell equations, when I say analytical equation, it means analytical solution, it means I can write my problem in terms of with a paper pencil method, some equations on the paper, and I can solve them using standard ordinary differential equation or partial differential equation methods analytically. That kind of solutions exist only for canonical shapes. When I say canonical, only for standard shapes. For example, here you can see an electric wire, or you can also consider it as a metal fiber. Some cylindrical object which has 2 or 3 layers of materials. So because it's a cylinder, I can write a differential equation in cylindrical coordinate system, and then I can apply boundary condition for the inner material and outer material and everything analytically, and I can solve this problem. So I do not need any computer to solve it. However, if the shape of my wire is like this, on the right side, it's an object which is not of a canonical shape. It's a weird shape. There is practically no way to solve this boundary value problem using paper pencil method. So what we do at that point, we need numerical approaches. So to do numerical approaches, we need to discretize all these electromagnetic equations into a proper numerical method, using some proper numerical method. And now, when I say numerical method, it means there will be a lot of choices of methods to solve that problem numerically. And we will be able to solve this problem using some computer and by choice of our numerical method computationally. And hence the field computational electromagnetics. And if you are doing it only for the visible part or for a photonics device, you can also call it computational photonics. But for the sake of generality, let's call it electromagnetics. And the applications of such computational capability are huge. Like every device or every structure we have today, which uses any form of electromagnetic wave, at its design stage, the designer or at its use or its analysis, the designer or the analyzer needs to see how the electromagnetic wave will behave when it impinges on any of these objects. And now these objects, as I said, sometimes these objects will be much bigger than the wavelength of the wave we want to simulate it at, or sometimes they will be much smaller than the magnetic wave which we want to simulate that certain problem. So this brings a range of possibilities, and computational electromagnetics deals with that range of possibilities. So, so computational electromagnetics becomes a multidisciplinary area. So there will be biomedical engineering and biotechnology devices. Also deal with the interaction of electromagnetic wave with the device, physics-based signal and imaging systems, even the computer chip design. In a computer chip, there are millions and billions of points in the to each other, and then there will be some route to do that. However, there are million routes like that, and there is an electronic signal flowing through those wires. Let's call them interconnect. Now, when an electrical signal passes through any wire, we know from the electromagnetic knowledge, it also radiates. And that radiation depends on the shape of that interconnect and the frequency at which we are dealing there, and all kinds of aspects. So to design a computer chip, for example, and then I can say chip where we have optical interconnects, where one part of the device wants to interact with the other parts of device through some optical interconnect. That optical interconnect itself will also radiate. So there needs to be whole analysis at the design stage that whether these interactions of different interconnects will be useful or will they be harmful for the overall operation of the device. And then that's how we have to change the design and we have to optimize the design. And similarly, all these electronics devices, MEMS, and also NEMS, nano electromechanical devices, which are becoming more useful in applications. And similarly, at the radio frequency level, remote sensing and subsurface sensing, where we want to see if there is some certain kind of object or material hidden under a surface which I cannot see visibly, but an electromagnetic wave may be able to see that object under some surface, let's say Earth. So there is some object which is hidden in the subsurface of Earth. So electromagnetic wave should be able to see it, but to do that, you need computational capability to optimize your design. And similarly, electromagnetic compatibility and interference analysis, which is required for all kind of, let's say, electronic user devices. And similar kind of, let's say, compatibility and interference analysis is required at practically all wavelength regimes when we are designing a particular device in that particular wavelength regime. So that requires compatibility analysis, which is a computational electromagnetic area. And similarly, in the communication, it's antenna design. And here, in our discussion today, if we are doing photonics, so in photonics, we deal, and when we say metaphotonics, which is an area which I'm sure Professor Qasim and other speakers have talked about, we are dealing with nanostructures of certain materials, and we align those nanostructures together to make a device. So that each of that nanostructure is a nano antenna, and you can assume that nano antenna equivalent in its function just as your mobile phone antenna. So both of these things, that nanostructure which forms your metaphotonic device and this antenna which sits in your phone, for the purpose of electromagnetic simulation, for the purpose of computation electromagnetic, both of them are two different antennas. It's just that their size and the wavelength at which they operate, they differ. But mathematically, for a Maxwell equation, it's the same kind of boundary value problem. It's just at a different frequency and maybe a different boundary condition. So before I proceed further, so I want to also highlight that why the knowledge of computational electromagnetics is important in multidisciplinary education of today, these days. So, because in this workshop we have been talking a lot about STEM, and when we say STEM, so we are talking about STEM education which leads to novel technology. And novel technology requires knowledge of modern tools, and computational electromagnetic is one of the modern tools to enable all that. So there has been this nice discussion article, and I have highlighted some of the points here, and it's written by some of the very well-known people in the electromagnetics and photonics domain, that there has been some over-reliance on the commercial electromagnetic simulators these days, that our students, especially the graduate level students or the senior design level students, they have to spend a little bit more energy to understand more of the basics of these computational tools, which they find very easy to use. However, they may not be doing in the best possible way. So what the highlights from this article, which I want to convey here, is that majority of our students at some point will rely on some of the commercial electromagnetic. It can be FICO, it can be ANSYS, it can be numerical, CST, COMSOL, these kind of tools. Now, we as educators have the responsibility to ensure that our students have some degree of familiarity with these tools. That's what we do always. We give them assignments, they do simulate some of the design problem which we give to them using COMSOL, using CST and everything. However, there is this possibility of misuse or over-reliance, because these commercial tools are made user-friendly. You can make any geometry and you can put any boundary condition. So if the user is doing it without knowing the underlying knowledge, and it's not an intelligent use, then the output they are getting may not be correct. So CEM knowledge, computational electromagnetics knowledge, will enable, if this knowledge is available, will enable the users, meaning students in this case, enable them to make an informed choice among the solvers available. So it happens most of the time with all of us. We give a certain we assign a certain simulation problem, and the student suffers in the start which tool I should use. So mostly it happens that there is some particular tool which the lab has been using always, and they try to simulate each problem on that tool with that particular setting. What we want to show here is that for each problem, there can be a different requirement, and that different requirement of computational tool can bring benefit in terms of reduced time in the simulation and increased accuracy if we know exactly for this kind of problem what simulator or what simulation approach will be best. So the basic training in some of the widespread computational electromagnetic methods can build the basis of the solid and optics and photonics education. So that's the message which can be deduced from this discussion. Now, because the language which we are talking here, I like when ICT and they say everyone speaks one common language, science. Here, for the sake of this discussion, everyone, whether they are microwave area or the optics or photonics or even the high frequency, X-rays and gamma rays and ultraviolet and all that, we have one thing common, which is Maxwell equations. And when we want to solve Maxwell equations, we can do it in various ways. So here, I have, in this brief summary, what I want to show is that those four Maxwell equations can either be solved in frequency domain or time domain. Now, frequency domain versus time domain Now there is a whole things which can be said here, but obviously, if you have to solve your problem at one particular frequency, the natural choice should be frequency domain method, because you can input a certain frequency and the solver will solve that problem for that particular frequency. However, if you need to solve a problem for a range of frequencies, a frequency domain method will need to repeat that simulation for each and every single frequency, and this will take a lot of time. So imagine a student who wants to simulate a nano antenna, for example, or some optical lens, and wants to see behavior of it for a certain range of frequencies, and he has a frequency domain solver. He might need to repeat that simulation for each wavelength or each frequency of interest. However, in time domain, what we want to make sure that student knows is that in time domain, you can design a time pulse and you simulate your device for that particular pulse. And that pulse, when transformed into a frequency domain through a Fourier transform, inside you are actually simulating the behavior of your device for a full range of frequencies. So you send one pulse and you receive that pulse, and then you take the Fourier transformation of both pulses and you can compare, and for a range of frequencies you have your result in one single simulation. So two major differentiations are frequency domain versus time domain. And when we do time domain or frequency domain, so in frequency domain, because we already are into frequency, it can be low frequency or high frequency. So for the purpose of optical simulations or for the purpose of photonic simulations, most of our problems, all of our problems actually are considered as high frequency problems. If the wavelength of light or wavelength of the electromagnetic wave is much smaller than the size of the problem. For example, you want to simulate the effect of electromagnetic wave when it let's say red color light, which is wavelength is in nanometer. That red light, when it impinges on a building or on a wall. Now, that wall is somewhere in meters, and the wavelength here is in nanometer. So your problem is 8 or 9 or 10 orders higher than the wavelength. So in this case, some of the electromagnetic properties of light can be ignored. For example, polarization arguably can be ignored. So in this case, you are only interested that the light impinges on that on that structure wall, and it will reflect in a certain direction. So we may only do the reflection analysis, and we know that that material does not absorb, and also we can neglect the scattering. So in this case, high frequency, which are geometric optics and physical optics, and all optics people or optics students, they're familiar with them. And then if you go into further bifurcation, there can be geometrical theory of diffraction and physical theory of diffraction, which can explain these methods. However, if you want to simulate that same red light, which is wavelength is in nanometers, that how this light travels through a graphene sheet. Now that graphene sheet is also in terms of size in nanoscale. So your light wavelength and the device in which you want to do the simulation, now the size is comparable. Both wavelength and wavelength of the light and the size of that device is comparable. In that case, you cannot use geometric optics or physical optics. In that case, it's a low frequency problem, meaning you cannot ignore the certain aspects of electromagnetic wave like polarization, which I was saying. You actually need to solve the vector nature of the Maxwell equations. And hence, to do that, you can you can divide your method either on the basis of integral equation, i.e. here, or differential equation, meaning that equation any differential equation can be converted into an integral equation. So now it's up to us whether we want to solve that problem in the form of an integral equation or a differential equation. Now, there is a whole range of cost-benefit analysis here. whether I should use an integral method or a differential method. So if I am interested in a problem which has just one material, and it's a large size area where I want to simulate the behavior of electromagnetic wave, and I am only interested in the boundaries of one particular material, it could be of benefit to use only the integral equation method. However, if there are layers and layers of different materials and they are stacked together, in that case, integral equation and the limits of the integral to solve the problem will become too messy. You will never be able to solve that. However, in a differential method, you can, because differential or derivative, as we know, by its nature, it's a local method. Like you take derivatives at a certain point. Integral is on a boundary. So if your problem is simple, you can integrate the problem on. However, if your problem is complex, you can take derivatives locally. So you have multiple layers of materials stacked together and it becomes your device. You can go to each point and take the derivative of Maxwell equations and use the finite differencing method or any method which we'll discuss, or finite element, or anything which can solve that problem in a differential approach. So depending on the nature of the problem, you can choose between differential versus integral equation method. And then within differential and integral, now it also depends, are you in frequency domain or time domain? There are certain methods. So the famous one of them are finite element method, which is a frequency domain method, and it's a differential in nature, finite difference method. And similarly, another famous method is method of moments, which is an integral equation method. Time domain, the famous one is finite difference time domain method or transmission line method, etc., etc. So for a given problem, our commercial tools mostly have a choice of several solvers within that simulator, and a user, from his knowledge of what he wants to simulate, what kind of problem he has in hand, can choose between those methods and use those methods efficiently. And in some cases, the problem can be of a hybrid nature, that my device has some parts where there are a lot of materials involved, a lot of different materials involved, and then there is some part where there is only one fixed material, and then there is another part where there are several materials involved. I might use two different kinds of solvers together to solve this problem. And that can be done in hybrid methods. And when we do hybrid, then of course, using the numerical techniques, we can also decompose our bigger problem into smaller problems, hence domain decomposition and that kind of thing. So our commercial tools, they try to fit all kind of simulation problems into certain categories, and the solver will try to implement that simulation using that primitive approach which is already there. But that may not be the best approach. If you know your problem, you can improve the accuracy, or you can also speed up the process. Or in some cases, you may not be able to get the simulation. The problem is even complex. So as I will just quickly skip through because I have been told I will finish at 1 p.m., which is like we have 4 minutes. So I will not go into too much details, but I will stick on the message that what things are important. What things are important when we pick certain simulators. So just a reiteration here, this discussion I did just now, is low frequency versus high frequency. So high frequency are the problems where wavelength of the problem is wavelength of the electromagnetic wave which you want to impinge is much smaller than the size. This is the problem. This is the example where I was saying we impinge light on a wall. Wall is much bigger than the wavelength of light. Now, in this case, you can use physical optics, you can use geometrical theory of diffraction, and I'm sure in one of the Professor Mahmoud Qasim's lectures, he also discussed ray tracing techniques. Those techniques can be used only in the cases where wavelength of the light is smaller than the size. However, if you want to simulate a problem where wavelength is almost equal to size or comparable, like there is a difference of only 1 or 2 orders, when I say 1 order times, for example, then the structural dimensions are on the order of wavelength or smaller, then the polarization of the light cannot be ignored, meaning the vector nature of the electromagnetic wave has to be considered. So all known methods like finite difference time domain, finite difference frequency domain, finite element, method of moments, etc., they all are vector nature problems, and they are good to go for low frequency. Another term which you will come across as students when we started to read some papers in the optronic simulations, so people will use simulated problem using full wave method, or we simulated this problem using a scalar method. So the difference lies here. When we say full wave method, it means the vector nature of the light or the electromagnetic wave has not been sacrificed. So that method is a full wave method. So finite difference time domain, method of moment, boundary element method, they all are full wave methods because they do not make an assumption, like in ray tracing, for example, that the polarization of the light impinging on the wall, the polarization can be ignored. There is no such distinction. So full wave versus scalar. So most high frequency methods we can say are scalar methods, and the low frequency methods we can say are mostly full wave methods. Sometimes we also use a term rigorous method, and that means that it's a method, it's a numerical approach in some parameter. That parameter can be, for example, I want to simulate this object, and this object has when I discretize, I create some mesh around it. Mesh means I will discretize this object into smaller pieces. Now that mesh size is a parameter, so I can control that mesh size to be smaller or bigger to improve the accuracy of my simulation. If the mesh size is small, then I will discretize my object very nicely. If the mesh size is bigger, the object size will be simulated in a rough way. So now this method has a fine-tuning parameter here which can control the exactness of that simulation. So these kind of methods we sometimes also call them rigorous methods, because there is a resolution parameter which can improve the accuracy to the point that if you fine-tune your resolution nicely, you can get a result from rigorous method which is almost same as exact method. Now, it's a new term I haven't written here, but exact method means when I solve my equation through paper pencil method, ordinary differential equation or partial differential equation on a paper pencil method without any computer, that is the most accurate solution for that problem. So sometimes the rigorous method can give you for canonical problems the same result as the exact method, and this is how we actually determine the accuracy of any simulation we are doing. We simulate a canonical, known, simple problem, exact solution of which is known, and then we simulate it using all of our methods, and then we keep comparing how close are the results we are getting. So I will skip through some of the less important slides to stay on the message. So which method we can use? So any of these methods can be forced to solve any problem. However, we can improve the accuracy and reduce the time by a nice selection. So here I will show a numerical approach using integral equation, which is very famous. So just to give you a flavor, how any of these methods work in practical. So for example, I want to simulate a metallic let's assume this is an antenna, and you can consider it, for the purpose of this discussion, it can be a nano antenna being simulated at an optical frequency, or it can be a large size antenna being simulated as a microwave frequency. The problem remains the same. So to solve this problem through integral equation, we start from Maxwell equations, And then we apply boundary conditions. And boundary conditions is actually the shape of the geometry here. And then in this case, I want to use method of moments. So we apply boundary condition on the surface of this metallic object. We know the boundary condition is that the total field at the surface of any metallic object should be 0. So to implement this boundary condition, we come up. There is a whole way we will not go in the discussion. We can come up with an equation which you can see is in an integral form. And that integral equation has a Green's function involved, and that Green's function actually defines how the electromagnetic wave will interact through the background to this object. Now, that Green's function, you can imagine it as for the system people, it's a transfer function of this system. So this Green's function will be very important. If we are in free space, this Green's function will take different form. If we are in a dielectric or a layered dielectric, now depending upon the object's properties, this Green function can change, but overall the integral equation will look the same. Now, to solve metallic objects, like in this case, to solve the metallic objects, an integral can be built based on the electric field boundary conditions, or sometimes on the magnetic field boundary conditions, and sometimes both electric and magnetic field boundary conditions can be applied together. In this case, we call it combined field integral. So this is just to show that in method of moments, the problem, before it reaches a computer, how we develop equations mathematically and later discretize them. So, however, one of our consideration is when we do the simulation, when we run the simulation at the end, when I will code all this into a solver, when I run the simulation should be accurate. Simulation should be accurate, and also it should be fast. It should not take days and years to simulate. So it should be in a practical regime. So what I want to show here is that before we even apply the numerical approach to the analytical equation which describes that problem, that analytical description itself decides that whether, when we discretize this method and build a solver based on that, that solver will be fast or accurate or not. For example, electric field integral equation is known to be most accurate for any problems where any problems of conducting nature, where electromagnetic wave sees a conductive body in front of it. Or in case of light, you can say when light, like visible light, sees mirror kind of properties at some object. Now, electric field integral equation will be accurate. However, the convergence due to resonance issues will be low. Now, if you build a solver based on electric field integral equation, it will take forever to solve some kind of problems. Magnetic field integral equation, on the other hand, is known to be less accurate. However, it has a better convergence and it has no resonance problem. I will resonance problem. However, now we can consider that this problem slows the convergence rate if there is such issue. Now, in natural choice, we want our problem to be simulated in a most accurate way. Accuracy means when I do the actual experiment, the actual measurement, and the simulated result, they match in a best possible way. That is accuracy. So I want to have best accuracy, and I want to solve my problem in the fastest possible way. So what we do is, in this condition, and this is now regarding method of moments, what we do is we combine electric and magnetic field integral equation due to their benefits, and we do a trade-off here. So magnetic field integral equation plus electric field equation, and then we do some scalings. And we build up a new formulation that will be a trade-off between convergence. Similarly, if the problem is dielectric nature, we may need to combine electric and magnetic fields together. So now the formulation of the problem will get more and more complex. So if I want to show here, so what we do in a typical electromagnetic solver design or a solver on the back end relies on some formulation. So here I'm showing that formulation. So once you finalize that formulation, we implement that and we code it, and then that becomes a normal computation tool which we all use. Now this tool can be in-house if you code it yourself, or the commercial tools have done this already, and you just need to know that how it is done and how to access in those tools the certain resolution parameters or certain formulation choices given in that tool. So here, sometime we have problems, meaning we have a simulation to be done, which takes longer and it's not accurate using commercial tool, but we can do some ad hoc in-house. So we can generate some in-house simulator, improve formulation. So an example will be shown here, which is a variation of electric field integral equation into a dual surface electric field integral equation, which resolves the major issue in electric field integral equation, which was of slow convergence. So this will be a formulation. When I show this will be a formulation which is accurate as well as it will converge fast. So now it's better than all the standard techniques, for example. So coming back to how this discretization happens. So I was saying that we finalize a formulation depending upon whether it's integral or differential. So when in your solver you can choose integral versus differential, it means you are flipping the method. So once you have the formulation, then you discretize it. And there are standard method is we use a Galerkin method, and that Galerkin method actually converts your integral equation into a set of algebraic equations. And we know algebraic equations can be written in the form of matrices. So in this case, this was a linear thin wire, and this thin wire has to be simulated for some input electromagnetic signal. And so we have splitted this wire into 7 smaller patches, and each of this patch has a certain algebraic equation, and we solve the algebraic equation simultaneously. This is how the problem gets discretized and converted into a form where a numerical method can solve it. Now, if we do it in a straightforward way, it depends the time the simulation takes and the memory required to do that kind of simulation on a system depends on how you discretize it and how you are developing your method. So just to show, if I have a problem which can be meshed, sliced in n smaller pieces, for example, this wire was sliced into 7 small pieces. So if I have a problem which can be divided into n cross n smaller pieces, we need systems in our computer which is of the order n square, And to solve a matrix of size n square using direct solving, we know from linear algebra, a method like Gauss elimination, the scaling of the problem is n cubed. If I increase the size of my problem, if I, for example, double the size of the wire I want to simulate, the requirement of CPU time will increase by Q. So if my size is doubling, then the time will not double. Time will go 8 times, 2Q. And the storage will be square. So the storage requirement in RAM, memory requirement will be 4 times, etc., etc. So now we use all kind of numerical techniques to reduce the time and memory put. So Krylov subspace iterative solvers, we know from linear algebra, they can be used to reduce the solution time from n cubed to at best n square. And in some cases, we can do some further tweaking of the problem based on some physical assumptions And I call those methods fast methods, where we can reduce the memory requirement from n squared to linear. N or sometime n to power 1.5, meaning if I increase the size of my problem, the memory requirement will scale linearly. And I will show here why this is required or why this is useful. And similarly, the storage time should also increase linearly. So those kind of methods are known as fast method. So you might have seen in the commercial solvers which inform them that the method they are using are either fast multipole method or multi-level fast multipole method or adaptive integral method or integral equation FFT based method. So the reason being is on the left it's computation time and on the right it's memory requirement. So if you see on the left, the number of unknowns are increasing. And CPU time is on the y-axis. So the black line here is the direct solution, which we all know in to solve the algebraic equation. Now, if the number of unknowns are 100, for example, and they increase from 100 to, let's say, 1 million, for 1 million cross 1 million matrix size on a simple CPU, this simple inversion will take 31 years on a simple Intel i5 computer, let's say. However, if you can solve that method, not on a direct solution, but through an iterative method, that time can reduce to 1.16 days. Improving through a fast algorithm, it can reduce to, let's say, 8 minutes, and then in a best linear method, that can reduce to 6 seconds. So at a time when we want to use computers, it was of interest historically to come up with methods which can reduce the computation time. However, sometimes the computation time was not a bigger problem. The bigger problem was memory. You need to load that certain matrix which you want to solve into a memory, and that there will be a whole process. And typical computer will not have a memory of 8 TB, for example, even today. So for 1 million cross 1 million matrix, if we use direct solution method, it requires a memory of 8 terabyte. However, if you can use a fast algorithm, you can use iterative trial of subspace method. This can be reduced to 80 GB, and in case of n log n scaling method, 640 MB, or in a linear method, which is the ideal, it will only require 80 MB, and a simple computer should be able to do that. So, however, so one of those fast solvers, so just to show how these fast methods are developed, one of those fast methods is applied on the electric field integral equation, where the Green's function of electric field integral equation is splitted into Green's function samples and Lagrange polynomials using mathematical techniques. And the benefit of doing that was, for a given problem, you can discretize that problem into certain points, and the interaction of any 2 points on this object, we do not need to know all interactions. We only need to know the distance between the 2 points. So for example, distance between point 1 and point 2 is same as distance between point number 4 and point number 5. So we only store the Green's function based on the distances, and we do not store the whole Green function. So this saves the storage, and this also saves the computation time. So I will skip, however, we can do this, but this will compromise our accuracy. So another thing we do is that for points which are too close to each other, we do not want to do this kind of approximation. So we split our matrices into near field interactions and far field interactions. So this way we are not compromising on the accuracy, but at the same time we are improving the simulation time. So, as I said, you can do your own formulations to improve the problems in where you see that the commercial solution is not available. So, for example, here we worked on a dual surface method, where the electric field integral equation has been extended to include the surface to resolve the resonance problem. So, just to quickly mention what is the resonance problem. If we want to simulate in using method of moments any problem which is closed surface, it can be, let's say a cylindrical object, which is a cylindrical cavity, for example. Now that cavity is a closed surface, and mathematically integral equations are known to be unstable due to inherent resonances which can appear due to the closed nature of that particular size, and that slows down the convergence of the problem. So what we do is that we apply additional boundary condition in an inner surface, call it a dual surface. There will be some computational in that, but that resonance will be resolved. So just to show how we validate these computational methods at the time of development, so each computational method is tested for convergence and accuracy. In this case, we are saying the dual surface integral equation method can be used for closed surface. However, for example, the sphere is a closed surface. It has a certain resonance problem at certain frequencies, but a dual surface has no resonance. Also test any of solver we come up with, we test them on canonical shapes and also some test benchmarks. So some useful benchmarks are sphere, square, this is a NASA, there is a practically, so these are at microwave frequencies. However, the same theory applies on the optical side also. So this sphere here, so MIE, mean scattering, we all know. So we know the exact solution of this particular object. So if we design a solver which can give you the same result as mean scattering theory, it means your solver is accurate. So we do the testing on mean. We also do the testing on a cube. Cube has certain corners, and it is of interest to see how the solver behaves at those sharp corners. And similarly, this NASA element has both effects. It has corners, it also has the circular effect on the other boundary, and up to so on. So what we are showing here is that this dual surface method works effectively, efficiently on all these benchmarks. So it's a practical method to use. Also, one could think of a problem where there are closed and open objects both. So in that case, it might be of interest to use standard electric field integration on the open objects, for example, these red portions, and we only use the dual surface in a blue portion where there is actually an interior problem existing. So just to show you the usefulness of having computational capability in-house, what kind of benefits it can bring, something like that. So in this case, some UAV, and this size of this problem is 15 times the wavelength at this problem is being simulated. Now, if we use standard, in this case, this is FICO, the CPU time is 17 hours, 12 minutes to solve this problem, and the memory requirement is 15 GB. However, if you come up with your own solver, we have proven that it's accurate also, but the CPU time has reduced to only hours, and the memory requirement is 5 GB. It's a better computer, etc. You can bring this to the practical limits. Like I can wait, to simulate a certain problem, we may not be able to wait for several hours. Similarly, the same method, this is what I want to show here for the optical and photonics application side. Now, the similar kind of method of moment through this FFT method, which I was showing, is applicable to nanostructures at optical frequency regime. So in this case, in this project, we were working with Boston University at a project where they had these aperiodic nanostructures. So now these aperiodic nanostructures, so in these structures, if you want to simulate them in a commercial solver, the problem is these are aperiodic. So we cannot use approximation. So in most of the numerical console CST simulations, we assume a simple structure and then assume it's periodic. So that periodic approximation can help a lot. However, if the problem is aperiodic, so in this case, these are 5 10,000 nanocoins, and each of these nanocoin is actually plasmonic. This is a plasmonic device. So each of these coin is made of gold with diameter of 50 nanometer and thickness is less than that. And these are arranged in a Vogel spiral arrangement. They come in this beautiful shape. They bring some very useful properties. It has been shown in experiments. However, when we want to simulate, no commercial solver will be able to simulate this big size problem, which is 60 times of wavelength, in a reasonable time. So what we show here is that, for example, this simulation, when done on numerical, it took 101 hours, which is more than 4 days, and the memory requirement was 80 GB. On the other hand, if we use ad hoc solver, which we developed by doing the approximation based on the known physics and known properties of this problem, the CPU time was reduced significantly to 8 hours and the memory requirement was 18 GB. So in practical device design, we can improve the design of the device if we are not limited by the limitations put by the commercial solver. For example, commercial solver requires that you can only simulate periodic structures. So the designer will not use aperiodic structure. However, it is known that if we can use a periodic structure, the overall performance in this case of this device will be much improved, etc., etc. So these are some examples which I have shown. And so in the interest of time, so I have been told that I wanted to show also some of the novel fractional formulations where we can club these known computational electromagnetic techniques with the fractional calculus methods, and so that these techniques can be applied to more complex type of problems. So, for example, I just want to show one, and then we will move on. Then I will close and I will go to questions and answers. For example, one known problem. Is, for example, laser interaction with the surface, with a rough surface. So in the theory, we know there are certain methods where we can simulate a rough surface. We cannot simulate a rough surface in full wave approach. So most of the times we only rely on the experiments or some approximations. So in this case, you can see here is a rough surface and there is a light impinging on it, and we want to know how much the light absorbs or reflects, or etc. So what we do here is that I will just take 30 to 40 more seconds. So what we do here is that the roughness at this structure, we use some fractional analytical approach where we assume that this roughness can be modeled as a fractional space, meaning a space where the dimensionality or the degree of freedom for the electromagnetic wave or the light is a little bit reduced. So we come up with a hypothetical space which is fractional in dimension. So the dimension of that space is not 1, but less than 1. So this poses some new question that how electromagnetic wave behaves in a space which is fractional in dimension. So we did a whole mathematics before, and in the form of monogram, how Maxwell equation can be written in space of not 1, 2, or 3D, but any fractional d, 1.5D or 1.6D, etc., etc. So if we are able to do that, then we can actually compute the Fresnel coefficients at free space to the rough. Now the rough structure is actually this hypothetical fractional space. So we compute the Fresnel coefficients and the reflection and transmission parameters. So when we did that, we computed the and then we took the actual rough surface, the image analysis of that to find the fractal dimension of that rough surface, and then we were able to show that each rough surface can actually be characterized with a fractional dimension number, and if you use the fractional Fresnel coefficient at that particular number, the experimental measured result was shown to be equivalent to what we simulated based on our fractional model. So this kind of approaches can be useful if you are able to do a hybrid approach where you can include the fractional based of novel techniques and the problems which were considered rough and disordered, they could be dealt with easily in the simulation room. So I will stop here and I'm open for the questions. Thank you so much for your attention.
Thanks, Dr. Zubair, for your time and a nice talk. So, floor is open for questions from the audience. Okay, I think I will go for one small question. I mean, the things you have hard for solvers, right? So can you just comment upon like modern techniques, AI integration into this kind of solvers, how they can be beneficial? Because we had some sessions on AI driven design and optimization, like how it is different from and how it can help further optimize the design cycle.
Not go over that material in this presentation due to time. However, there is a continued interest to incorporate AI methods to improve the simulation time and in certain kind of problems. And there are becoming physics-inspired neural networks which can be very useful in the solution of partial differential equation or in some cases integral equations on which these methods rely. It's a work in progress, and in the future we will see that that the computation time can be brought much lesser, not for generalized problems, but I would say these techniques are useful for ad hoc nature of problems where you know that your device's shape is known, you have only one device, you have to simulate that device each time again and again. You can train a neural network or an AI method to come up with analysis, or sometime to come up with design in an inverse problem, which can be fabricated and tested in much lesser time. And we have done that before for the case of solar thermal photovoltaic device, where a meta surface is designed to improve the absorption on top of that photovoltaic cell. And we were able to come up for that particular kind of meta-optical device. We were able to train a network to propose the exact arrangement and exact sizes of the nanostructures, which can give you the best efficiency in that scenario.
Chat window. Are you able to see? Hello? 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 Hello?
Okay, so I have a question here in the chat. What would happen in computational physics simulation of graphene when we use effective thickness of 1 nanometer instead of 0.34 nanometer? Does it affect the reality of the research work? Yes, so graphene simulation is always troubling. So in terms of, now it depends at what wavelength you want to simulate your graphene structure. So we know that a single layer graphene is atomic thickness. However, if the wavelength at which you want to simulate it, that wavelength is 600 nanometer, let's say, and we are considering 200 to 1700 nanometer, for example, in this case. So if you consider the thickness of at which you are simulating it, is still, it's not comparable, but it's still within 1 order. Within one to two orders. So there will be some there will be some effect on the accuracy, but theoretically it should not be much. However, it also depends what kind of approach you are using for graphene simulation. So in some cases, we treat graphene as an equivalent impedance layer. In that case, there is no thickness involved. You can use that approach. Like there is free space, then there is no layer thickness. However, there is a boundary, and that boundary has a certain impedance. And that certain impedance, the experimentalists have already found out what impedance is there for graphene at that particular frequency or wavelength. And then you will be out of this thickness issue. However, the closer you keep the thickness in the simulation to the actual one, the most accurate your result will be.
Is there some more questions from the audience? Seems no more questions. So with this, let's. Okay, I think no more questions. So let's thanks again to the speaker. And thanks.
So in the after lunch, we will go to the lab to finalize the work. Then tomorrow in the morning, we will have one lecture by Malik Massa. So don't miss. Then after that, we will have the closing ceremony where you will get your certificates. And finally, we go to the village.